rather than feeling asleep. I think there is a tea break after 1 hour, so you can have garma garam chai. But before that, please try to keep you awakened. Alright, so today we are here for the post lunch session for our SPARC workshop, SPARC 3. And now, you know that in the morning we had a mesmerizing talk deliver presentation from Professor David Field, and followed by Professor Satyam Suhas from IISc. Now we will continue on texture presentation on texture, talk on texture related thing, because the workshop is related to texture, but it's a little bit different flavor compared to the earlier one. Here we will listen from Dr. K.S. Suresh. He is from IIT Roorkee. It's a very famous place, academically as well as environment also. Roorkee is a very nice place, right, to roam around and go for some religious places. Everybody knows that. So Dr. Suresh is going to talk about how to determine the texture from X-ray diffraction, XRD plots. X-ray diffraction everybody are aware of here. Okay, bachpan se, from your undergraduate. What is X-ray diffraction? Indexing the XRD pattern, VCC, FCC, where the some peaks are visible, some peaks are omitted, HCP, and all this. Now today, this topic, Dr. Suresh is going to focus on how to deal about the texture, how to know the texture of the material from their X-ray diffraction itself. Okay, welcome. So welcome, Dr. Suresh, for your valuable lecture, so that we can learn from that and student can enjoy the lecture much. Okay, please start, Dr. Suresh. The platform is yours.
Yes, sir, we can hear you.
Okay, thank you very much, Professor Shampa, and I also like to thank Professor Somje for inviting me to deliver this lecture. So in the morning already you have gone through lectures from different experts. So as a quick recap, we will see first about the representation of orientation in terms of pole figures and what is mean by preferred orientation, and then go to the today's topic for pole figure measurement using XRD. So in this, I will briefly mention about the instrumentation, what are these 5-axis goniometer, and the role of background and defocusing corrections. And towards the end, we will see 2 case studies in what ways textures could be different in some metallic materials. So already Professor David Field as well as Professor Suhas have mentioned these things, so let it be a quick recap. So many a times while dealing with crystallographic texture, we think about the textures in rolled sheets. So that's why, like I have shown here, the arrangement of a unit cell on a rolled sheet. And as you can see on this figure, the 001 plane is parallel to the rolling plane, and 110 direction is parallel to the rolling direction. So this particular HKL UVW, what we call it as the texture component, can be represented on multiple pole figures in different ways. So on a 100 pole figure, or a 111 pole figure, or 110 pole figure. So it can be represented on any particular HKL pole figure. But then I would like to draw your attention, since the plane 001 is parallel to the rolling plane, you will always notice on the 100 pole figure, at the center of the pole figure, you will notice a spot. Whereas on the 111 or 110 pole figures, so those planes are not parallel, since this is a single crystal orientation, so you are not observing. On the other hand, if you look at this 110 pole figure, and since our rolling direction is parallel to the 110 direction, so you notice that there is a spot corresponding to the RB. Similarly, there is another example wherein 112 plane becomes parallel to the rolling plane, and say 1 bar 10 direction becomes parallel to the rolling direction. Now this particular one, as you can see, you have some uh, closed dots as well as open closed circles as well as open circles. So the open circle represents the parallel planes which are occurring in the southern hemisphere, something like say bar 1, bar 1, 2 and so on. And since neither the 100 or 111 planes are parallel to the rolling plane, you don't find anything at the center of this pole figure. On the other hand, the 110 tag direction is parallel to the rolling direction. So you see a spot corresponding to the R. So now when we say about preferred orientation, meaning that certain orientations occur multiple times in comparison to other. Now, if we take a single crystal where you have only one particular orientation, so this is one extreme. So as such, there is no preferred orientation. We have only one orientation. Now, the other extreme comes where you have a random polycrystal. There is no preference at all. So all the orientations occur in a random manner. There is no particular preference. So the preferred orientation or crystallographic texture comes in between, where you have a set of orientations which have more preference in comparison to other orientations. So some of the application for single crystal include, say, the blades used in jet engine, and most of our other materials, whatever we use, they are mostly the polycrystalline materials. And some of the applications require a very strongly preferred texture, or in some case a very weakly oriented texture, so that we met a required properties. Again, I would like to draw your attention for this selected area electron diffraction pattern. So in a single crystal, you will observe a spot pattern, and in a polycrystalline material, you will observe a ring pattern, whereas for the textured material, provided if you are covering sufficient number of grains, so you will see an arc pattern. So I am starting with the electron diffraction because compared to the X-ray pole figures, many a times people are more familiar with these sort of electron diffraction patterns. And another thing I would like you to remember is that, so here we have marked two axes, A star and C star, which are indicating the reciprocal lattice vectors. So diffraction phenomena can be easily understood using a reciprocal space rather than real space. We will come back to this particular concept during this 5-axis goniometer. So again, this example I lately noticed that Professor David Field has already given, because this is one of the very early applications of texture, wherein the deep drawing of aluminum, which initially had this problem of earring. So depending upon the orientation, you can have these 4 types of ears, or sometimes 6 types of ears, based on what orientations you have. And that drastically restricted the extent to which a sheet can be deep drawn. As you can see here, so with the different examples, so these scans have been drawn to different extent. So now depending upon to a what particular extent you can extract, so if I can extract to a larger extent, so I can use a smaller weight of the material to hold the same amount of food or fluid whatsoever. So this has led to a really a 25% cost reduction, and we don't use so much in India these days. However, in other developed countries, So nearly 80 to 90% for soft drinks as well as for hot drinks. So these sorts of beverage cans are mostly made out of the deep drawn aluminum cans. Now one can do this texture measurement for bulk metallic materials or other materials also using multiple ways. The X-ray diffraction is the most commonly preferred method because X-ray goniometer is more easily accessible than other counterparts. While if you talk about neutron diffraction or synchrotron diffraction, so that may not be readily available at all the places, only at a few locations all over the world. Such sophisticated facilities are there, and so one has to wait for a long time to gain access to these things. While ultrasonic methods are more easily possible, however, they have more an indirect measurement of the preferred orientation, and later you will see for micro texture measurement, that is a local preferred orientation using either as EBSD or TM, maybe tomorrow from other different experts. So in today's talk, we will focus mostly on this X-ray diffraction, how it can be used to measure the preferred orientations. So in a X-ray diffractometer, so we have an X-ray source which gives us a monochromatic or near monochromatic coherent X-ray beam, and then these X-rays which are coming out of the source are made to fall on the sample at a particular angle using a set of optics, and then the X-rays which are scattered from the sample, so they are collected to the detector by the detector, and before they are collected it also goes through a set of diffracted beam optics. So from the X-ray source as the beam comes out, and what is the dimension of this X-ray that is falling on the sample is of one of the important aspect, because depending upon the grain size what you have, so we would like to cover a larger area so that at least a few thousands to tens of thousands of grains are exposed by the X-ray. So most of the heavily deformed samples, they have grains in the range of few microns or submicron levels. So therein may not be a problem to expose it to a larger number of grains. However, if you talk about cast metals or alloys, or these days additive manufacturing is a more popular technique, and these materials developed through such techniques will have a much coarser grain size. So then to cover a much large number of grains, it becomes an important and crucial aspect. So what is the size of the beam that is falling on the sample is quite important. Now this is decided by the slit opening in front of the X-ray source. So and apart from that, it also helps us to restrict the divergence of the beam. So once the X-rays comes out, they will like to diverge in all the directions. So then if the divergence angle is large, then at what angle they fall on the specimen, there will be a larger difference. Now one can go for narrower slits wherein the incident angle is controlled very precisely, but then it has a drawback of much lower intensity, as well as get you cannot expose it to a large number of grains. So because of that, for measuring pole figures, people prefer a slightly larger slit opening. Again, that will be decided by the dimension of the sample what you have, rather than a narrow slit which will provide a much accurate peak position. And then when we talk about the beam profile, so in X-ray diffractometer, you have two different ways in which X-rays can interact with the sample. In one case, you have parallel beam. In the other case, you have para-focusing beam. So as you can see from the terminology, parallel beam indicates that, so all the X-rays which are coming from the source, so they are in a parallel line. So all of them will have the same incident angle. Whereas in the parafocusing case, you are going to have a slight divergence of this incident angle. while parallel beam is more useful for the case of thin films as well as where you need very precise lattice parameter or peak position cases. For heavily deformed samples, parafocusing would provide a better way simply because deformed samples will not have the unit cell arrangement in the same fashion everywhere in the grain. There can be variations of unit cell arrangement within one single grain itself from the grain center to the grain periphery. So that when you are using a parafocusing beam, you have the ability to bring more number of grains into diffraction condition. So for the same reason, people also go for the residual stress measurement sometimes with this. So in parallel beam, you have all the X-rays are very well aligned, while parafocusing gives a slightly diverging one, but it could provide a relatively higher intensity for bulk samples, but it provides much lower intensity when you talk about thin films or when the volume of the sample is less. So now we will go to the X-ray pole figure measurement. So typically these are done using a texture goniometer, which are configured with 5 axes. Now the first 2 axes everyone knows, which are used to set the diffraction condition. These are nothing but the theta and 2 theta. Theta is the incident angle and 2 theta corresponds to the diffraction angle. Now the third angle, known as the chi, tilts the specimen plane with respect to the focusing plane. So the objective for this particular tilting is to determine the inclination of the HKL plane with respect to the rolling plane. So in the first case, from the 2 axis of theta and 2 theta, we will fix these positions for a particular HKL plane. And then the tilting of the sample with respect to the focusing plane happens, which is the third axis. And the fourth axis is the phi angle, which spins the specimen about its normal. So the relative rotation of the HKL plane at different chi angles are done. For instance, we will start with 0 chi angle and then go for a phi rotation of 0 to 360 and then take the chi angle to like tilt this sample to 5 degrees and then once again carry out the phi angle rotation from 0 to 360 degrees. So this third axis tells us about like how a given HKL plane, how it is tilted with respect to the rolling plane. So a combination of chi along with phi will help us to determine what is the UVW direction. Now the fifth axis oscillates the specimen under the beam, and this will be highly important if you have a very large grain size, as in the case of welded samples or additively manufactured samples or cast samples. So when you have a larger grain size in terms of hundreds of micron or larger, so to bring a larger number of grains, so we need to cover the required area on the sample. So this may not be possible with the highest or the largest opening in front of the X-ray source. So during which along the X and Y axis, one can oscillate the sample so that more and more number of grains can be brought into the Bragg diffraction condition. Now we will look one by one. So how these are done, say in a real experimental setup. So in this particular case, let me show you the cases of like the incident angle theta and the 2 theta. So most of you already know about this, but just for the sake of completion, let me go about this particular case. So here you have the X-ray source which is fixed constantly, and this whole thing which is rotating, that is the X-ray goniometer. So that carries the sample. The sample is fixed on this holder. Okay. So the sample keeps rotating at an angle theta with respect to a fixed X-ray source. The source is on the other side, and what you see in between is the laser focus, which is useful to fix the height of the sample. So it is again like tilting back. Now when you look at the other one, so we are changing the position so that and only one thing is getting rotated at a time to understand it better. So now this detector, which is rotating at an angle of 2 theta with respect to the source. Now during the acquisition of the pattern, so both the source, both the sample location as well as the detector will keep rotate with respect to theta and 2 theta for the source. Since this particular setup, the source is fixed and sample rotates at an angle of theta and detector rotates at an angle of 2 theta with respect to the constant source. Such type of diffractometers are called theta 2 theta diffractometers. So you may have seen other diffractometers wherein the sample is fixed while both the source and detector rotate at an angle of theta with respect to the sample. So those are known as the theta theta diffractometers. So by carrying out this scan, we can acquire a 2 theta scan for this particular sample. In this case, I am showing for a rolled aluminum, and you can notice multiple peaks, and these are also being indexed. Now to get the complete information about the orientations in any sample, it is not sufficient to have only one pole figure. We need more than one particular pole figures. So for the cubic sample, one needs at least 3 different pole figures. So which are initially taken as the first 111, 220, 200, but in this particular case, because this is heavily rolled, the 200 peak is missing. But you can see the 220. While the 200 peak is missing when the sample is placed at without any tilting, but once you tilt, one can still see the corresponding 200 peak also. For the case of BCC metals and alloys, instead of the 111, one will go for 110, 200 and 211 peaks. But see, the 111 peak as well as the 222 peaks, they will have the same information. However, we avoid to measure the 222 peaks, which are the higher order peaks, simply because the corresponding intensity is much less. Now, one more thing you have to keep it in mind that, so while acquiring such patterns, we don't always get the baseline at 0, but at some significant counts values. So this also one needs to keep it in mind while calculating the final pole figure. So we will see in due course of time why do you need 3 different pole figures for a cubic material, and this number increases to 5 different pole figures for hexagonal crystal system and about 7 for all other crystal systems. So now once you have acquired this one, say for instance, if the 111 peak is occurring at an angle of say about 44 degrees, so we will keep the 2 theta position at 44 and theta at 22. So half of that value. So after that, we will go for the tilting of the sample about the chi angle. So this angle is known as the chi angle, which tilts the specimen with respect to the focusing plane. So now you can see that the sample is getting tilted on this goniometer axis. So this goniometer allows to tilt the sample from 0 degree to 90 degree. So 90 degree is when the sample surface becomes completely horizontal, and 0 degree is when it is vertical. So now what happens is, this is like a vertical this is a horizontal diffractometer. So when the sample is at 0 degree tilt, so all of the X-rays will focus on this surface. However, when it goes to the 90 degree where the sample becomes completely horizontal, so only the top layer of the sample alone will be exposed to the X-rays. The penetration depth of the X-rays when the sample becomes when it is tilted to chi 90 or when it is becoming horizontal, that drastically reduces. So that is why we cannot tilt the sample up to 90 degree to get a meaningful information. Rather, we will restrict it to 70 or 75 degrees. So for the remaining region, we need information from other pole figures. Now, what is the meaning of this tilting of this sample, say from 0 degree to 90 degree? That is, if I look at the stereographic projection, when the sample is at 0 degree tilt, so we are collecting information for that particular pole figure at the center of this pole figure. Now, as you keep tilting, so we are going to travel along this direction. So when it is 90 degree, so we come to the periphery of this stereographic projection. But then we cannot get sufficient intensity over here. So we almost stop either at 70 or 75. So in each pole figure, some of these informations which are at the periphery of this stereogram, something is missing. So to compensate for this missing information, we need additional pole figures like 200, 220 in the case of FCC, and similarly for BCC, it will be 110, 200, and 211 and so on. So that is the reason. So now while tilting along the chi-axis means that we are traveling along this direction from the center of the stereogram towards the periphery. Now the fourth one, again, so what this particular thing going to bring in reality is the grains which have their HKL plane parallel to the sample surface will undergo diffraction. Now, there may not be the case like all the grains will have their HKL planes. Say in this particular case, now we have fixed for the 111 plane because our theta and 2 theta are fixed at say 44 and 22 degree angles respectively. So now we are expected to get the diffraction only from the 111 plane. So not from other planes. So if we are having a single crystal, then on that single crystal sample, the 111 planes are going to be parallel to the sample surface. But when we are dealing with the polycrystalline material, we will have multiple grains where the same 111 planes are tilted with respect to the sample surface. In some grains 5 degrees, in some grains 20 degrees, in some grains 30 degrees and so on. So the idea for this tilting is to bring those grains which have their 111 planes which are tilted with respect to the sample surface, those also to bring into the diffraction condition. So this tilting helps us to bring all sorts of 111 planes from 0 degree tilt to 70 or 75 degree tilt angle to bring into the diffraction condition. So this is the job for the chi tilt. Now the next one is the phi rotation. So I kept the chi tilt at 45 degree to have the better view, and now the sample is being rotated from 0 to 360 degree about its surface normal. So during this particular process, we are going to travel along the azimuthal angle for this in the stereographic projection. So for instance, if I keep a single crystal sample, okay, at a constant chi, so how this phi rotation is going to give me the information. Assume that at the given chi tilt angle, say we have one particular HKL plane which is undergoing the diffraction. So I am just rotating the sample about its surface, about its normal. Okay. So what is the sort of intensity variations in the detector one can expect? So by rotating this particular case, say here I am showing for a substrate with having a silicon 220 orientation on which a shape memory thin film has been deposited, which is also having a 022 orientation. Now you see that you have both the substrate as well as film. So they are giving multiple peaks. Now, what you can notice is that these peaks also have equal angular spacing between them. So they are about like sort of like 90 degrees between them. So this tells us like something about the symmetry of the material what we are dealing with, but it also raises the question, so why such multiple peaks are occurring, why the intensity is not constant throughout. But before we figure out this particular answer, let us say take a bicrystal wherein say we have grain A and grain B. Both are undergoing diffraction, but then the grain B is rotated with respect to grain A, say by 50° in plane. So now what you can see is that both the grain A gives like 4 different peaks and grain B is also giving 4 different peaks, but they are displaced by an angle of 55°. So as I told you, like this relates to the symmetry, but now to understand it further better, we need to go for the reciprocal space lattice, and before that we will just look at the simulated electron diffraction pattern. So here you will notice like two different diffraction patterns are given, one for the BCC lattice along 001 and another case for the FCC lattice along 111. Just for the sake of comparison, I have given these most famously used cubic materials. Now, when I say we are rotating the sample about its surface normal, so what we are going to do is like on the electron diffraction pattern, so we are going to travel at a constant distance from the direct spot. It is equivalent to the electron diffraction pattern as if we are going to travel from the direct spot at a constant distance. So then we will be traveling along all of this say 110 type reflections. So all of these 110 have the same d spacing. So they are at equidistance from the direct spot. So now we are going to see like these sort of different 4 peaks corresponding to that. However, if I do the same thing for the case of a FCC lattice, so wherein my beam direction becomes 111. So now instead of 4 like here, you are going to have 6 different diffraction spots. So corresponding to the symmetry what is typically located along the 111 axis. So similar thing happens in this case of X-ray diffraction also when we are rotating along this phi rotation. But now these sorts of things may not be clearly visible if you are dealing with a polycrystalline material, but only when you are having a single crystal or a bicrystal, it becomes more easier to observe these patterns, and that too when they are aligned, the diffractometer is aligned particularly to get these sorts of specific symmetric related information. So now why such a thing occurs? For this, let us go back to the construction of the evolved sphere and reciprocal space. So assuming say the real space vector is given like this, wherein A, B, C relate to the unit cell vectors and N1, N2, N3 corresponds to the number of unit cells along each of these base vectors. Now if we are going for the reciprocal space, so now instead of ABC, we have A star, B star and C star, where A star, the reciprocal lattice vector, is defined in terms of the real space vectors by B cross C divided by the volume of the unit cell. Similarly, the B star can be defined as C cross A divided by the volume of the unit cell, and similarly C star will be defined as A cross B divided by the volume of the unit cell. So by definition, so A star becomes a perpendicular to real space vectors B and C. So these points now corresponds to the reciprocal lattice space, and then we construct an imaginary sphere which was proposed by Ewald. So that's why this is called as the Ewald sphere. So this imaginary sphere has a radius equivalent to 1 over lambda, and the Ki here indicate the incident X-ray lattice vector, and Kd relates to the diffraction lattice vector. So the difference between Kd and Ki relates to the GHKL, which is the diffracting vector given by HA star plus KB star and LC star, where HKL are the Miller indices for the particular plane which is undergoing the diffraction event. So now when we have constructed this particular one, all the points in the reciprocal space which are intersected by this evolved sphere. So they are going to give the diffraction peaks. So that is what is going to happen when we are rotating along the phi axis. So that's why like you get 4 peaks when you have for 4-fold symmetry, and if you have for a 3-fold symmetry, because of the inversion this, you will get instead of 3 spots you are going to get 6 different spots. So this is the reason like why we are going to have this multiple one. So a combination of this phi rotation along with the chi rotation allows us to get both the HKL and UVW. So the chi will tell us by what angle the HKL plane is tilted with respect to some reference axis, and by locating the multiple peaks along the phi helps us to identify what is the UVW direction which is parallel to the rolling direction. So just again to revamp this one. So we are going to travel along this particular one. So if we have a single crystal, so you will see 4 distinct peaks. Say if I am having a say 010 or 001 oriented single crystal. On the other hand, when you have a textured polycrystal, instead of 4 sharp peaks, you will see a broader peak. Again, depending upon the kind of the plane which is having the preferred orientation, you may have only 2 broad peaks if it is there 2-fold symmetry, if the HKL plane is having a 2-fold symmetry, or you may have a 4 broad peaks if the HKL plane is having a 4-fold symmetry, and so on. Whereas in the case of a randomly oriented polycrystalline material, so in the phi rotation, you may not observe any noticeable peak. The intensity will be almost flat as if we are traveling around this particular. It is equivalent to that. Now we have always some difference between electron diffraction to X-ray diffraction because of the geometry, how it is happening, and also because of the case of like the wavelength differences involved between an X-ray diffraction to that of the electron diffraction. So finally, just a overall quick recap of what we are going to deal with here. So first, initially I start from the center, which is at chi equal to 0, and do the 360-degree rotation. So from this point itself, I am doing about a 360-degree rotation. And from there, I tilt the sample by an angle of 5 degrees. And with this 5 degrees, again, I keep rotating about a 360 degree. And once that is complete, so from 5 degree, now I move on to 10 degree and then make another complete 360-degree rotation and so on till I reach 70 degrees and so on. So beyond 70 degree, we are going to have very less intensity, so which is corresponding to the changes in the geometry of the X-ray profile which is falling on the sample. Assuming, say, I have a circular opening in front of the X-ray source, so that circular opening will remain circle at chi 0 degree as well as when we have the 2 theta as 90 degree. But most likely, like, you won't go this to 2 theta to 90 degree, but always you are going to have at a smaller inclination. At smaller inclination, the circle is going to be in the shape of an ellipse, and when we are tilting along this chi axis, this ellipse also gets tilted. So now what is the outcome of this particular event? So at a larger 2 theta and low chi tilt angle, all of the X-rays are going to fall on the sample. Now as I am going for a lower incident angle or a higher tilt angle, since the shape of this profile, the X-ray beam, what is supposed to fall on the sample, becomes larger and larger, you may come to a case wherein some portion or a significant portion of the X-ray beam falls outside of the sample. So now initially, if I say like there have been thousands of X-ray photons are falling on the sample. But at this tilt condition of say 2 theta at 20 degrees and chi tilt angle of 75, so instead of 1000 photons, maybe only 200 to 300 photons are going to fall on the sample. So the remaining photons are falling outside the sample. So we are not getting a very similar, or we are not treating the sample similarly when we are at lower theta or 2 theta angle to higher tilt angle. So this needs some corrections, what we call it as the defocusing correction. So based on the assumption, like, so once you have a circular opening, or one can also do it with square or rectangular opening. So, and then we has to make certain corrections. So how much of the X-ray photons are going to fall as you move or the tilt the sample along the chi, as well as you are increasing the 2 theta from higher angle to you are reducing the 2 theta to a lower angle. So these are called as the defocusing corrections. And apart from that, one should also do the background correction. So if you remember, initially I mentioned that in the beginning, so our background is not always going to start at 0, but it's going to have some pre-defined values. So this one needs to subtract, and then we also need to do, depending upon the chi and phi for a given 2 theta, this again changes needs to be applied. In addition to that, depending upon the incident angle, the amount of X-rays what is being absorbed in the sample may also vary. So that absorption is also should be taken into account. Now, once you do all of these things, and then using the orientation distribution function, now by taking into the factor of all the three pole figures in the case of FCC or cubic metals, we can get the complete pole figure information. So now this is a 111 pole figure for a well annealed nickel sample. Now you can see that the RD and sorry, it should have been TD. So the RD and TD directions have been marked for the 111 pole figure. So what does this 111 pole figure represent is how the 111 planes are aligned with respect to RD and TD directions. And you can see like there are iso intensity contour lines given by different colors. So the colors say starting from 1 to sort of higher one, they have more meaningful values. So if the iso intensity contour, that value denotes to 1, then it implies that the probability of finding these orientations are equivalent to the probability of finding a random orientation. On the other hand, say if I say that, say this pink color is represented by an iso intensity value of 8, so then the probability of finding these sorts of orientations are 700% higher than the probability of finding a random orientation. So their occurrence is 700 times more than that of the random orientation. So that way also goes for all other iso intensity values which are indicated over here. So depending upon whatever is the highest number over here, that is going to indicate the strength of the pole figure or how strongly the given material is having the preferred orientations or a texture. So now I will like to say few things like as a case study for two different samples. In one case, we will go with hot rolled medium carbon steel, and again this sample, the texture has been measured at two distinct locations. One is at the surface of the sample, and in the other case the mid thickness region. Now most of the time, if one is supposed to represent the texture, then one has to measure the X-ray texture at the mid thickness region itself. Otherwise, the surface texture sometimes can be drastically different than that of the mid thickness region. Now, why we go for the mid thickness measurement of the X-ray pole figure? Because the rolling is a plane strain compression process. The deformation of plane strain is strictly true at the mid-thickness region, while at the surface one may see some effects of shear also. However, what is the role of these shear effects at the surface which are giving rise to the changes in the alignment or evolution of the preferred orientation also becomes sometimes of importance to understand how this deformation is happening. Otherwise, one has to polish the sample up to the mid-thickness region. Say for instance, if you have a 2 mm thick sample, you have to slowly polish it down to a thickness of 1 mm up to the middle of the sample and then measure the pole figure on the middle region. Now in this case, we have measured both at the surface and then gradually polishing it down to the mid-thickness region, and this is a 90% hot rolled sample. The rolling was carried out at 700 degrees Celsius. Now I am showing here the three different pole figures 100, 110 as well as 111. Now again, like you have this iso intensity contours, so which are represented like from one having the white to the dark red color having here the 1.8. Now at the mid thickness region, you can see that this high intensity corresponding to 1.8 is there, but it is not there at the surface. However, qualitatively, the appearance of different poles, and if you look at the shape of these things, they are very similar both at the mid thickness region and surface region. What it tells is qualitatively the evolution of preferred orientations are very similar at the surface and mid thickness region. However, quantitatively at the mid thickness regions, certain orientations they have a much higher preference to occur than at the surface region. Now what are all these one? If you remember from my initial slides, so when I say I have a 100 pole figure, and if there is a strong point at the center, that would indicate that you have correspondingly few grains which have their 100 plane being parallel to the rolling plane. While now if I look at the 110 plane, although there is something is still there at the center, but the maximum intensity occurs slightly at an angle of say about 40 to 50 range. You are having a spread of this orientations. So the maximum orientations, so these 110 planes do not have, or maximum number of grains do not have their 110 planes parallel to the rolled sheet, but they are rather tilted at an angle of say from 40 to 50 degree. However, you still have a few grains which have their 110 plane being parallel to the rolling plane. So now in comparison to 110, you have a higher number of grains which have their 111 plane parallel to the rolling plane, but in comparison to 110, so this intensity is less. So again, like one can say that, so here you have a majority of the grains have their 110 plane parallel to the rolling plane, and next to that you have a 111 plane parallel to the rolling plane. Now what about the directions? So here x-axis, the horizontal axis indicates the rolling direction, and y-axis indicates the transverse direction. Now as you can see, along the x-axis, that is the rolling direction. So on the 110 pole figure, you will see a stronger intensity, which is indicating that there are more possible grains are there who have their 110 direction, say being parallel to the rolling direction and so on. Now, in this particular example of a hot rolled medium carbon steel, we can find that qualitatively surface and mid thickness region have very similar pole figures, but quantitatively there is a good difference is there. However, it may not be the same for all the cases. Now I am going for a cold rolled nickel sample. Now just for the sake of showing the orientation distribution function, so instead of pole figures, I am showing the different sections of the orientation distribution function. So on this left hand side, you have for the subsurface region, and on the right hand side, this is for the mid thickness region. So subsurface region implies here just a few hundred microns below the surface region. So to avoid the direct effects of friction on the sample surface. Now again, you will see these are all for 50%, 80% and 90% cold rolled sample. Now this is for a cold rolled nickel sample. Now in this particular case, you will notice that the surface or subsurface region to mid thickness region, the texture is drastically different. So unlike in this particular case where the pole figures qualitatively you have a similar one, but quantitatively there is a difference. But for this cold rolled nickel sample, both qualitatively as well as quantitatively, you are having or observing a drastic difference in this texture evolution from surface to the mid thickness region. Now there are various factors which are going to affect such sort of evolution of this crystallographic texture. But again, like how or in what way one can make a meaningful from observing these is one has to look at these iso intensity contour lines. But again, please remember that here we are having a maximum level of only about 6, while at the mid thickness region we are having a maximum level of 12, just to distinguish a few weaker orientations which are also occurring at the subsurface region. Otherwise, many of the other orientations will not be visible if I just use a very similar color coding for both the cases. So the orientations is something corresponding to this has the maximum preference at 90% after 90% thickness reduction, while at the surface level, so those orientations they have, but then if you see the corresponding values are going to range from say between 3 to 5, meaning that so the appearance of these sorts of orientation at the subsurface level, they are about 200 to 400 times they have higher probability than the appearance of random orientation, whereas in the mid thickness region you have nearly say about 700 to 1100% higher probability. In the same way, one can also look how things are changing at smaller thickness reductions as well. So to have a sort of interaction with all of you, so I will stop my session over here and I would be happy if there are any questions from the audience.
So the session is open for discussion. If you have any question, yes.
Good afternoon, sir.
Good afternoon, please.
Yeah. Sir, I have two questions. Like at some
Yeah.
point you mentioned in-plane orientation. Can you please explain that? What is that? Which condition called? And also, I think there is something called out-plane orientation.
Okay. Yeah. So the in-plane misorientation. So what I mean is, say in this particular case, say while the substrate and film are like two different entities, like in terms of their chemical composition, but say assume like if these are having these exactly the same composition and if the orientations are same, then it becomes sort of a single crystal. Okay. Now in this particular second case, so the one layer is slightly say rotated with respect to the other layer, meaning that the unit cell arrangement say in this blue one, so they are tilted say by 55 degrees say with respect to the red colored one. So that is the in-plane misorientation. Now rather than that, I can also tilt instead of rotating the one of these planes, I can also tilt the plane either about say the one of the axis, say either the x-axis or y-axis. So those will constitute the out of plane misorientations. So out of plane misorientation also one can see, but again like it takes a little more experience dealing with understanding how the chi, tilt and phi rotations both operate. But this phi rotation is more easier to understand this in-plane misorientations, wherein both the planes have the same HKL plane, but say some reference UVW directions, they are tilted with respect to each other. So that can be easily identified using this phi rotation. That is what the example I have given here. So is that clear, or
Yes,
do
it's
you
clear.
have?
Yes, it's clear now. Yeah, thank you, sir. And another question was in slide number 13, what can be the reason? Yeah, here. What can be the reason
Um,
that we don't see intensity of 200 but 400 intensity is visible because both are essentially same?
Yeah, so thanks. Yeah, so you have figured this out. So I'm really happy about that. So ideally, like this 200 should have occurred, but again, that was some problem in this particular case with the setup, like how we have took this particular one. Ideally, like when the 400 is appearing, so there is no reason like why the 200 shouldn't appear. Actually, like there was something hiding in the path of the detector, so that was some sort of a misalignment of the sample. Yeah, so you are very correct that the 200 should appear even with even a higher intensity than what you are observing for this 400.
Yes, sir. Sir, if I can ask another question,
Yeah,
can you
yeah,
please
please.
go to slide number 9? There we see the diffracted beams in the upper figure. The diffracted beams are parallel. How the mirror is making it convergent?
Uh, okay, so the mirror again, it is sort of like, let me
Okay,
just
the
see
mirror
if
is
I
not
have.
flat. Is it some concave kind of
Yeah,
thing?
you have a sort of a curvature
Okay,
which
sir.
makes sure that at whatever angle it falls on, so the curvature decides that everything of this goes to the detector side.
Okay,
So
sir.
because like in it is not the mirror term like what we use through the glass. So these have some special coatings where the curvature is designed in such a way that whatever might be the incident angle of the X-rays on these mirrors, so the all of this like the way like they go, they are will be pointing towards the detector.
Yes, sir. And so
So this
last
is the
question.
geometry of this mirror. Yeah.
And one last question, what is the typical diameter of X-ray beams while taking texture measurements?
See, now it depends on the sample diamond, say, rather than the sample dimension, the grain size. Say, if you have grains of the order of a few microns, so then possibly like 1 centimeter by 1 centimeter sample is good enough. And in this 1 centimeter by 1 centimeter sample, say you can have an X-ray beam size of something like 5 mm opening, but definitely not more than 10 mm opening or 1 centimeter opening. Otherwise, like for most of the time, your X-ray is going to fall outside the sample rather than falling within the sample.
Thank
Okay,
you, sir.
but now if you have a much larger grain size, for instance, like if your grain size itself is several hundreds of micron, so then in that particular case, the 1 centimeter by 1 centimeter sample alone may not be sufficient, but rather you may have to go for say something like 3 or 4 centimeter, but then the opening in front of the X-ray, so in none of the detectors you have say more than 1 centimeter, or in extreme cases you can have about 2 centimeter also. But what then we will do is, so you see like here the axis along the horizontal and vertical one, the sample is mean to oscillate along this x and y axis, so that at any given point of time X-ray is made to fall on a much larger region of the sample. So although your opening is small, but by using a much larger sample for collecting the whole figure, so you can make sure that so multiple grains are always irradiated with X-ray to have some statistically meaningful data.
Thank you, sir.
So, anyone else have any questions? Yes, I'll come.
So, sir, you have mentioned about defocusing at high tilt angle, at high chi. So, what sort of means? He is not.
No, he's there.
Yeah, please.
Yeah, means what sort of defocusing means? it will become defocus at high tilt angle, or what? Or we have to do some correction at high tilt angle.
Yes, say assume that, say I have sort of maybe a square opening in front of the X-ray source. Okay.
Yes. Yes.
Now, if I keep my detector exactly opposite to, or sorry, not the detector, say if I keep my sample exactly opposite to this opening, then the same area of X-ray what is coming out of the source is going to fall on my sample surface.
Yes.
I hope you can appreciate that.
Yes.
But now that is not possible because that corresponds to a theta itself of 90 degree. Now when I am having like initially having theta of 20 degrees, 30 degrees and so on. So instead of like a square, okay, now what is going to have is now I have a kind of like rectangle shape of the beam is going to fall on the sample.
Okay.
So this is without any chi tilt, but just with the lower theta incident angle itself.
At lower incident angle. Okay.
Yeah, now when I am tilting the sample, so instead of this particular one, so what it becomes is like now you have changing into a kind of like a quadrilateral shape. So now at larger one, so your beam will be like initially at, if I can go for a theta of 90 degree, my sample area irradiated to X-ray will be the smallest one and equivalent to the X-ray opening.
Okay.
But when I'm going at lower theta and very high, so many of this X-ray photons now will fall outside of the sample. So initially, if I am using a majority of the sample for the diffraction event, now in this particular case, I am using only a small fraction of these X-ray photons for the diffraction event. So it is nothing about whether I have so many preferred orientations are here, but now I am not using the same amount of X-ray photons between these two different conditions. So this has to be geometrically accounted for the intensities what we are getting at lower 2 theta angle and particularly at higher tilt angle.
Okay. So second question, if in texture measurement we do not do phi rotation, only do chi rotation, and we do texture, will there be drastic difference or?
Okay, so see that one can do for like say in this particular example you had a point source. Sorry, it was a point source and a point detector also. So point detector means at a given location, like it can have only corresponding to one X-ray intensity alone. But I'm sure like at IIT Kharagpur, you have a line detector as well as area detector also.
Yes.
So with those two-dimensional detector, so the need for this rotating about 360 degrees and also going along the chi tilt for every 5 degree tilt is also not needed. So rather what you can do is you may just collect at 2 or 3 different chi tilt angle, because at any given point of time you are covering say a much larger region of the stereogram or the pole figure. So in this point detector at any given point of a time, say you are going to collect say only at this particular spot alone. Okay, but if you have a line detector, possibly depending upon how you are oriented the detector, you can going to cut a similar range of this intensity. But when you have the area detector, so how much information you are going to collect, it becomes larger.
Okay.
So by that way, so you need not to have for like every 5 degree of chi tilt, and similarly for all the pi rotation going from 0 to 360 degree. So you may need to rotate, like keep only at say 5 or 6 specified chi and phi combinations, and then you can cover almost most of this information what is there. So because of that, the texture or the pole figure measurement using the 2D detector reduces like almost 5 to 6 times than what is typically done say using a point detector. Say For a point detector, for individual pole figure, you may need about 30 to 45 minutes of time. Whereas the 2D detector, say within 20-30 minutes, you can easily cover pole figures of not even 3, even 4 or 5 pole figures also you can cover. So that is the advantage of having the 2D detector.
Okay.
Yeah, thanks for raising this question. Because of the lack of time, I didn't go for multiple types of detectors, but good that like you raised this question.
Okay.
Thank you, Suresh. Is there any more questions? I think there is no questions, so I would say that it was a very nice presentation, Suresh, and we are very glad that you took our invitation and presented it online. It helps us to make this symposium very successful. I hope that your presentation gave our students.
Yeah, thank you, Professor Biswas. Thank you for inviting me. So, yeah, it was also a good experience, like being connected with the textile community. And I really appreciate your effort for organizing this workshop. Thank you.
My mic actually got off, so I stopped in between. So Professor Field is sitting here. He says hello, and to camera ghoro na. And Professor Shivan
Yeah,
Roy is sitting
I
here.
can
He
see
says hello.
Professor Shibayan Rai. So yeah, my
Yes. And if you move the camera, you can see camera move karo. You will see Professor David Field sitting here. He is willing to say he's liking to say hello to you.
yeah, hello, Professor Dave. Yeah, good to see you at least virtually. Yeah, so I would also like to have you sometime at IIT Roorkee. So possibly next time, yeah, when you are visiting, we would like to invite you to our Roorkee. Thank you.
Thank you, Suresh. Thank you.
Yeah. Thank you all.
We are benefited from your talk. Thank you so much. See you then. So we will go for a short, very short tea break. Okay, so there is tea. I already tasted it. It's good. So you you should go and immediately come back. And then Professor Shivan Roy from Material Science Center is going to give a talk on, I think it is texture and titanium.
হ্যালো 1 2 3 4 পক্কা ব্যাটারি একটু কম আছে কার হেলমেট এটা হেলমেটটা কার
ঠিক আছে এবার চেক করে নাও বলে হ্যাঁ হ্যাঁ এখানে আসছে না এই ভিকি ভিকি সোর্স ফোর্থ 4 নম্বরে সোর্স এসছে কিনা দেখো তাহলে এটা ডুপ্লিকেট করতে হবে। আর স্যার ওটাকে একটু ডুপ্লিকেট করুন স্যার।
কিছু করার নেই। উইন্ডোজ বি স্যার, উইন্ডোজ না, এটা উইন্ডোজ না, এটা ম্যাক। এটা ম্যাক। স্ক্রিন মিররিং হবে। আপনাদের কোনো ইয়ে আসছে না, এটা অটোমেটিক্যালি দিয়ে দেবে, কানেক্ট হয়নি।
আসেনি তো সিগন্যাল।
না সেটা ঠিক আছে, শো অল রেজলিউশন কিন্তু আপনাদের ডিসপ্লে মানে 1920 by 1080 ওইখানে ড্যাক একটা ডিভাইস আছে তো ওই রেজলিউশনটাই না। হ্যাঁ কিন্তু এটা এখন অবধি ডিটেক্টই করেনি, সেটাই কথা, এরিয়াকে ডিটেক্ট করে। পাওয়ার আছে তো?
হ্যাঁ ওখানে পাওয়ার আছে।
কেউ কি ল্যাপটপ থেকে প্রেজেন্ট করছে না?
না স্যার।
তো এখানে যদি 1920 by 1080 আসছে ওটা না না, আপনার ইয়েই আসছে না, এখানে আরেকটা তো দেখাবে তো আপনার সেকেন্ড এলে তবে তো আমি চেঞ্জ করব। ডিটেক্টই করছে না কোন রকমের ডিসপ্লে।
বিকে ওই সেকেন্ড যে ল্যাপটপ যেটাতে ইউটিউব চলছে ওটা
আপনার এইটা
খালি
এটা
HDMI-টা কাজ করছে কিনা দেখো।
আচ্ছা সেটাই, এই HDMI পোর্টটাই কাজ করছে একটু দেখুন। তা এখান থেকে কম্পিউটার থেকে খুলে দেওয়া যাবে, এখানে যে কম্পিউটারটা আছে?
না স্যার ওটা খোলা যাবে না। দেখো নিচে, চলো বের করো বের করো বের করো।
বাট এটা স্যার মিরর হচ্ছে না, দরকার নেই, এক্সটেন্ডে চলে। ঠিক আছে এক্সটেনশন
ঠিক আছে বুঝতে পেরেছি। বুঝলে কি এই এন্ডটা লুজ ছিল, ডিভাইসের এন্ডটা ঢিলা ছিল, কেউ খুলেছিল মানে ঠিক মতো ঢোকাইনি। স্যার আপনি কি বসে দেবেন না?
না না না, আমি
তাহলে আপনাকে একটা ল্যাপেল দিয়ে দিচ্ছি ওয়্যারলেস।
হ্যাঁ ঠিক আছে, আমি আগে এটাকে কানেক্ট করি প্রেজেন্টার।
Check 1 2 3 check 1 2 3 check 1 2 3 check 1 2 3 না অডিয়েন্স দেখতে হবে না। হ্যালো চেক এখন বলেছিলাম অফিসকে পোস্টার লাগাতে, তো না দিলে
ব্যাটারি কি এখানে পাওয়া যাবে?
ব্যাটারি তো বলো, ডেনিস যদি এসে থাকে ওর কাছ থেকে নিতে কালেক্ট করতে।
এটা
এবার ঠিক আছে। হ্যালো
ডাবল
হ্যালো দেখো শোনো ওখানে গিয়ে। হ্যালো চেক হ্যালো হ্যাঁ কি নেই? হ্যালো চেক 1 2 3 হ্যালো চেক ঠিক আছে তো? কেন বেশি বাড়ালে আবার পিক নিয়ে নেবে।
ঠিক আছে।
Okay, good afternoon again. So this is the second presentation of today's afternoon. Shivan needs no introduction. Uh, uh, Dr. Shivan Roy he is working in IIT Kharagpur in Material Science Center, right? And his expertise is related to titanium, related to texture, bioimplants, aerospace, and phase transformation, I suppose. He has done a lot of extremely well reviewed research and has lots of good publications, and we are privileged that he has come here with this invitation to present on the topic which is related to titanium microstructure and texture evolution, right? So maybe it involves phase transformation and variant selections also. So we welcome him. Let's welcome him. And please, Shivan, come. And the dice is yours to present. Thank you so much.
Yeah. Hello. Hello. Okay. Yeah, that's good. Fine. So I need my slides. Yes. So thank you, Somjit. Nice introduction. So Somjit and I, we go a long way. So that's why I may not be needing an introduction for him, but I may be needing for others, definitely. So when Somjit told me about this workshop and I agreed, I didn't anticipate two problems. And those two problems are, most of the other speakers are presenting very basic fundamental things. So they advantage that possibly they are teaching slides they were presenting. So compared to that, mine will be focused.
It is good. It's a change.
It's a change, yeah.
We need this change.
Yes. So this is one caution. It may appear to you a little bit unfamiliar. It's possibly a little bit focused topic, although I tried to go as basic as possible. And second problem, that only yesterday Somjit told me not to present anything unpublished, which I normally do not do. I like to present unpublished work rather than published work. You can go through your papers and just read about it. So unpublished things are more fun to present in a community. I mean, that gives me a chance to sort of consolidate them and trying to understand them better. But that's why I had to basically change many of the things in the presentation from yesterday. So anyway, so unlike what the topic was mentioned in the poster or in the schedule, this is a little bit different. So I thought I'll tell you about importance of microtexture. So the name microtexture itself is very, very interesting. I'll tell you why. But before that, actually, as I said, I was just planning to present some unpublished work, recent work and all. So that's why the contributors, my students, their names are there. But then, of course, two of them are here, Arjun and Soumya. I am not allowed to present their work because it is unpublished. They are continuing. And Shovik is my first PhD student. Yes, some of his work I will be definitely including. So he's a contributor. He's presently at GE Aerospace. And but he also has unpublished work which I will not be able to do. Anyway, okay, this one is not working again. Okay, fine. Maybe I can just try to do this. Yeah. Okay. Excellent. That's about me. So just to tell you that, so I and Somjit, of course, was very much contemporary in the same group with our PhD at ISC. I had a master's from IIT Kanpur and BTech in ceramics, and I joined IIT Kharagpur at 2015, and before that I was at various places doing my postdocs and afterwards also. And while making this, I realized that this photograph I need to change possibly. Now it's at least 7-8 years old. Okay, so this is important, our research area, and these are some of the material systems. So I largely work on that structure processing property, this domain, and material systems, we mostly work on metals and alloys, and in that titanium, of course, is in the top, and we also work on aluminum. And very recently we are joined with a postdoc, Pankaj is here, so through him some high entropy alloy. And then another facet of our group's research is on ceramics, and there we have some very special ceramics, machinable glass ceramics and carbon fiber reinforced silicon carbide composites, and some work are completely out of any material. So one of them is like shear band formation in metals, and of course additive. Commonality of all of them is they are all structural materials and mostly space and aerospace materials, so you can classify them as a high temperature materials. If you want more information, please visit our group web page. And this is a poster that we are making at this moment. It is still incomplete. It basically shows the spectrum of various characterization and tools that we are using. So in microscopy, we are using almost from optical microscope to SEM to TM, high-res TM and all. We use microcity, of course. Just hope this works. Okay. This one doesn't work, so just make it work. 1 second. That's bad. Okay. So, so we work on microcity, we work with texture, high temperature, X-ray, various type of testings, mechanical testings, atom probe, and lots of other things. And now I am coming to a very general topic, that is microstructure. So what happens when I join to this PhD at ISC Bangalore with Professor Satyam Suhas as my supervisor, I had a very typical problem. That problem was the entire field was extremely new to me. There was nothing, I was not even trained as a metallurgist, so metallurgy field itself was new. And then the texture field was completely new to me. So it was difficult to appreciate the texture, and I will possibly go to there. And I think possibly from morning, since morning itself, you are hearing about importance of texture and various other things. But what it appeared to me is a little bit abstract. So it was not carrying a meaning as such. And the problem of that, what I realized, that it is because of the representation here, the representation of texture. This is what is the problem. So it was very much mathematical, difficult to connect something, and so up to here it is okay. I mean, you find out that okay, crystal reference system, sample reference system, these, that, what is happening with something like, if you have this orientation, this kind of things, you will have a property difference. All of these things was good, but the problem was the representation of texture. And compared to that, microstructure was easier to understand. I mean, you can see something if you, with your naked eye also, you can see, and seeing is believing at times. So that was much easier to appreciate. And as I said, I was a ceramist, and this texture was having a very little role in ceramics. Rather, microstructure was much more common to us. Otherwise also microstructures are interesting because they basically sort of completes this connection this structure property connection was very much, you can do it very easily with microstructures. So for example, I have shown you one work from aluminum alloys, not titanium, that you have some precipitates, nanoscale precipitates. When they are fine sized, nicely crystallographic, you can get a very high strength, and when they are coarse, incoherent, theta prime, theta prime, so you lose all of this. So it is very easy to appreciate that. Okay, something is happening in front of you. You do microscopy, you get to see them, something is happening. Compared to that, texture was a little difficult one to appreciate. As I said, particularly because of that problem, mathematical. And second thing was, what I was particularly problematic, as such I always try to ask questions why certain thing happen in the way they happens. So that was a difficult to connect in terms of texture, why certain thing. For example, I will tell you one thing which was very problematic for me initially. So we all see this rolled sheet and then the three different sample orientations and all, RD, TD, ND. Now the question is why we will consider only those three directions. What is the problem if I consider an axis which is 5 degree from rolling direction? What is so special about those directions? Why? It's a simple question. Fine. One answer is that's the symmetry. That's not the symmetry of the specimen as such. That's the symmetry of the deformation that you put there. That's why. Okay. So if you consider this rolling, which is a plane strain deformation, so you can imagine that something is pulling things in the rolling direction and something is pressing things in the normal direction. That's why these are important, correct? So this why things was very much obvious. Now the second why comes that fine, okay, I understand that this is related to the symmetry of that particular deformation system, then what? What is going on inside that is so important? So that those why things was difficult, and that's one reason of that is this microstructure which you can see and have a feel about it, and texture on the other side which you cannot feel, more of abstract. There was a lack of connection between those two. At least that's what I felt when I started way back in 2006 onwards and so on, that there was a connection lack between these two. And if you talk to people from earlier generation, I think Professor Field here, when they started, this gap was even wider. Although there were work, there are different work like recrystallization texture where people saw, okay, cube grains coming out in FCC, nucleation, growth theory, etc., etc. So there was a constant effort of connecting the microstructural phenomena with the texture development, but it was largely lacking at that moment. Not so much because fortunately when we were growing up as a researcher, this one fantastic technique was coming out, that's called EBST, electron backscatter diffraction, which was with that this term also started coming in, microtexture. So microtexture doesn't mean always that it is texture at the micron level. To me, it's basically the connection between a microstructure and a texture, okay, at a level which is within the microstructural level. Microstructural level we normally consider based on a length scale. Okay, now the definition of microstructure also has gone many different length scales. So the aluminum alloy that I showed you, for that it's not a microstructure, rather it should be called as a nanostructure because that's where it controls the properties. So the definition of microstructure is basically still we call it from the length scale itself. So EBSD was able to give you orientation at that length scale. Okay, that's the first thing and first advantage that we saw. And over the years, I realized many other advantages of EBSD. One of those other advantage I'll tell you, when I joined for my first postdoc at Germany, that was a mechanical engineering department. Now mechanical engineering department, mechanical engineers always had a problem with materials engineers. That's simply because mechanical engineers used to deal with quantitative data. Whatever data is given to them, that's in numbers. whereas materials engineers are quite trained with a qualitative data. Grain size is bigger, this is larger. How big? With respect to what? You will find this kind of things written. Grain size is bigger, so something is stronger. How big it is? That's the problem. So mechanical engineers were very much about quantitative data. And material scientist always believes in more or less qualitative data. Now this EBSD is one very good technique which gives you quantitative data, which somebody can use. And that is what? So if you look at in the property measurement space, again there only I got introduced to this very nice technique called digital image correlation, which gives you spatial distribution of strain. We normally tend to think strain as one single value. You do tensile strain and you get it. For them, it is better if you get the entire matrix. They talk strain or stress in terms of matrix, unlike us. So this EBSD was very good for that. And then when I joined for Oak Ridge National Lab, I realized that it is chemistry which is very important for controlling properties. I can go ahead and talk about that some other day, maybe with aluminum alloys. Chemistry is the most important controlling factor there for properties, for stabilization of those precipitates. This tend to believe me that microstructure, basically the way we are trained or we think, should be now broadly expanded, and it should now carry description about features. That features can be precipitate, grains, whatever it is, lamella, with a quantitative touch into it, size, aspect ratio. Plus, it should also contains orientation information. Fine, grains are okay. What is their orientation? How they are oriented with respect to something. And lastly, the chemistry of them. Okay, so microstructure should mean feature, orientation, chemistry, and maybe even more as we learn. But right now this is the definition of microstructure to us, to my group, and that's how we work. Okay, so this is more general. Of course, EBSD has many other advantages that I always like to explore. It gives you 3D information, three-dimensional orientation. Now you can get a coupled chemical information. You can get Kikuchi, TKD, transmission Kikuchi diffraction, which I have fascinating story to tell from my personal experience of doing Kikuchi. And you can do in situ testing and all those things. So many great things you can do. Now all of these things are good. I'll just talk about one general thing, and then I will move to more focused about titanium, which I'm supposed to talk. The problem of connecting microstructure with texture or whatever is this. This is called a representative volume element problem. That's one very big problem if you ever work with design engineers and so on. The point is, say you have to build up a big bridge. The civil engineers have to build a big bridge, mechanical engineer has to design it, and in their design they are using some property values, say of steel, which is determined of a sample of this size. Okay, a standard sample of this size you determine out of 3 maybe, okay, for better statistics, and that value is going and making that bridge. So you have to make sure that this testing that you are doing with this simple specimen at your lab should carry the same kind of information, that information you generate, which is valid for that larger structure. That's the problem with something called representative volume element problem. People who works with something like fatigue, I think Somjit works with fatigue. Somjit knows the difficulty of fatigue. Okay, so you just change your sample, same batch, same thing, fatigue life will be different, because one will contain a simple pore, another one will not. That severe it is. Now the data he generates from here possibly is going for making the bridge. So out of hundreds of fatigue testing, you generate one single curve, and that curve is used for your life over the bridge. It's as simple as. So this is the problem of microtexture, another problem, connecting microstructure with texture. Mechanisms that you are telling happening at a microstructure level is actually controlling the texture at bulk level or not. That's always a question. And I'm just bringing it up because this is particularly one of the point of discussion and all between once I was handling a project with GE Aerospace, and that's one sort of problem, how you have to generate data in a larger scale in order to say certain things. Okay, so you can see that this is basically an EBSD map, and you can see the large sized EBSD map. Top one is actually a PLM, polarized light microscopy. We were trying to connect these two, PLM and EBSD and so on. Anyway, so let's, I think general thing is over. Let's, huh? This one, the TI64. Okay, so let's come to general things about titanium alloys. Okay, so titanium, I like to call that it's a hero for aero. So because it's a very much aerospace application, titanium is all about aerospace. These days I am taking a material science course. You are just a general thing that all of us are hearing about jet engines, and India should build up a jet engine and so on and so forth. So other than many other problems and all, India is building a jet engine. I was once a part of, very tiny part of that initiative in one part of my career. One of the problem of making our indigenous engine is this materials. One part of the problem. To get this aerospace grade materials, aerospace grade alloys, certification of that is a very challenging issue. And titanium, so much so for titanium. That's why you will see this TI64, this one single alloy. It has a market share of 56% nearly of all titanium used till today, and particularly for aerospace application, because there is no replacement for it. Extremely difficult to replace. The properties are so well balanced, everything, certification particularly. It's very, very difficult one. If you put a search in the web, the most number of papers on titanium that comes is an improvement of properties with respect to TI64. So how to make this one alloy better, that's what it is, mostly. Okay? That's because titanium goes in very critical parts in the jet engines, and its specific properties are very good. In fact, it is it's kind of a little oxymoron when you say it's the heaviest in the light metal category. So we have 3 light metals, aluminum, magnesium, titanium. I work on 2. I don't touch magnesium because Somjit is there right next to us, who is an expert of magnesium. Yes, so 2 of us completes this light metal family, aluminum and titanium. He gives it to me. So these are the 3 light metals. Out of that, titanium is basically the heaviest and most suitable for aerospace application because of its temperature capability and so on.
I think titanium has
Higher specific strength, yes, of course. Regarding, and high temperature capability. The best thing is high temperature capability. Aluminum, magnesium doesn't have that. Okay, so that's fine. And titanium in general appears with HCP alpha phase. We call it alpha phase, HCP, and it transforms to beta, BCC phase at high temperature. Now this transformation, these 2 phases are related by crystallography, and I will be maybe talking a lot about this, the crystallography of this too. That's called Burgess orientation relationship. The black box, under the black box, that's what is Burgess orientation relationship. Titanium, of course, TI64 basically, that's an alpha plus beta alloy. So what happens? We can change this phase stability. We can tune it. We can add an alloying elements, usually heavy elements. We add vanadium, moly, this kind, niobium, this kind of heavy elements we add, and we stabilize this beta at room temperature microstructure, and then we make this alpha plus beta alloys, various type of. But primarily Ti64, for example, it is mostly driven, most of its mechanical properties are driven by alpha phase. It's highly anisotropic because it's an HCP, and it has, you can see the different type of slip systems that it carries. It is mostly Bessel and prism slip, but pyramidal slip may happen in certain cases. Some special cases it also happens. At higher temperature, titanium deforms much more easily because CRSS, you have more number of slip system available. Plus that beta phase volume fraction also increases with temperature. That helps at higher temperature. So all the thermomechanical processing of titanium alloy happens at a certain higher temperature. Room temperature, it mostly, there is a big role of twinning. So this is titanium, and this is mostly in titanium in the alloy space. If you just little bit move from that alloy space and add more of these alloying elements, most importantly is aluminum. So other than nickel, titanium also is very much friendly to aluminum. Okay, so nickel aluminum is like super alloys, same as titanium aluminum system, very important. So you move almost 50 towards 50%, or maybe a little bit. You just move out of the 6. You started getting an ordered intermetallic phases, which is called alpha 2. Then you move even further, and you started getting another intermetallic phase, which is titanium aluminides, gamma titanium aluminide. So these are ordered phases, intermetallic ordered phases. And then you have, so this is in the alpha stabilizer, what we call aluminum. If you move in the beta stabilizer side, again you started getting some other phases, various martensites. So titanium marten forms martensites, different type of martensites. One is hexagonal martensite, one is alpha double prime orthorhombic martensite. Plus you have some very unusual phase called omega phase as well. That happens with specialized systems. And other than that, there is a ternary system which is of importance, titanium aluminum niobium system. That also forms some specialized phases like B2, ordered B2, BCC phase. It forms something called orthorhombic phase. All of these are very, very interesting, but extremely difficult to understand and to work with. We haven't touched them till now, maybe some other time. Okay, we'll stick to alloy. We'll not go to this intermetallic domain at all. Just we'll stick to the alloy domain. Now what happens if I take this alloy and as I said, one great thing about this material systems which show phase transformation is that you can play around with temperature and strain, and you can generate various different type of microstructure and texture largely. So if you simply, I don't know why this one not working, otherwise I could have show you maybe even better. Sorry. So if you just simply change where exactly you are doing your heat treatment, you can change the microstructure. Okay, you can get something called lamellar microstructure, and you change that lamellar microstructure. If you do pointer? Yes, sir. It will be a pointer. चलो ঠিক আছে, আমি এটা থেকেই করে দিচ্ছি। Okay. So if you are able to change the just the cooling rate, you are not cooling it. If you cool it slowly, you will get what we know call it lamellar structure or colony structure or Widman-Staten structure. And if you cool it from the beta phase field, if you cool it down with a very fast quenching, you will be getting a basket wave structure. And these are two different completely. Basket wave we will not touch. I will not touch today basket wave structure. That's a completely different story altogether. So you will get a basket wave structure, acicular structure. Similar way, if you do this thermomechanical treatment at different temperature range, alpha plus beta, low alpha plus beta, high alpha plus beta, above the beta, you will be generating different texture. So that gives us a very good possibility of different type of texture microstructure combination which are needed for different properties. Certain ones are good for enhancing, say, creep, certain ones are good for enhancing fatigue, and so on and so forth. So you can just simply check different properties and their different applications, different need for microstructure and texture. Okay, so this is basically how titanium alloys are made. So they are, first you start with a, I think I will go there and that will help me to possibly at least show by hands. This is what you get it in a normal casting. It's called lamellar structure, large big grains. And then you carry out what we call typically ingot breakdown. That gives you much smaller grains and much finer colonies, lamella, etc. Then what you do, you do a secondary processing, alpha beta deformation. You are in the alpha beta range, lower temperature. You break down this lamellar microstructure and makes it equiaxed. Fine. So these are the basically more or less the secondary or the processing schedule. Largely there are many intermediate steps and all. About this structure, this is kind of most important ones, because you will be seeing most of the titanium component comes in these two variants. Either it's called, one is called bimodal structure, one is called fully equiaxed structure. Bimodal structure, we have two different type of alpha phases. One is called primary alpha stable, which is this large aspect ratio phase, and secondary alpha, which is basically transformed from beta, that is coming here within the transformed regions. They comes as a lamella. Now let us see, I will just divide these two. One is the beta deformation or beta processing, where you are coming from either with a castings where you have simple thermal effect, or you are coming after a beta working, which is thermal plus mechanical, but somewhere over here, and this side. And we will try to show you. Oh, this is called superplastic testing. This is another specialized. Titanium is very much used for superplastic forming. Most of the aerospace grade materials are formed by superplastic testing. So most of till aluminum alloy is the one which is used for superplastic alloy for the most part of the, all the fuselage that you see, all the doors that you see and all in an aircraft, they are formed by superplastic forming. And the next one is titanium. This one? Oh no, this is just a camera image. It's showing how nicely this, high temperature titanium is expanding. That's what. Okay. So let us first see the micro texture development in beta to alpha transformation. So this is a very busy side, this one. So if you think that texture evolution in texture formation in titanium is easy, you are not very wrong. That's the general idea. What max can happen? You have a nice orientation relationship. Okay. So you take something, take it to beta. The beta, I'm not going into complexities of what beta is going to do. texture, how the texture develops in beta and all, I am not going in there. But I am just saying in alpha beta transformation how it happens. So you have this nice guiding tool and you think that okay, if I take something to beta and come back, I will get this exactly nicely followed. So this is a stereographic projection of superimposed basically. You see it here. So this is the 0001 and 110, they are superimposed on each other. So that's how it should happen, correct? So if I use this and try to read it, beta and alpha, they should match. Let us see that. So I start with here, this is an as cast, I start with a cast material, simply do an extrusion on this, beta extrusion and come back. So this is the starting one, alpha, and this was the beta basically, and I come back. So if this has to be followed, if I go from here to here and come back here, this should be replicated, right, because this is going to beta and coming back, if I just think it in this way. Turns out that it doesn't happen, right, it doesn't happen. You go to from here to here, why it is or rather how it is not happening, what is changing and all, I am not going into that. Point is, bottom line is it doesn't happen. This one single thing doesn't really control or explain why you just do. You can do just a simple thermal cycling. You don't need to do an extrusion for this. You simply take this, take it to high temperature and coming back, where you started and where you ended will not be the same. Okay? That's the beauty of it. So one major reason or the major reason why it doesn't happen is because this relation itself. What happens, and if you see this is an EBSD of this extruded one, you see different colors, right? Now these different colors are present also in different amount and different size. These different colors basically tells you this. These are called the variants. If you look at closely here, this is a family of planes, right? We all know from our basics about crystallography, this curly brackets gives you family of planes. So those family of planes, once they become specific, then it gives you some different possibilities, which we call variants. So one single beta, if you start with like this, if you start with the single beta, it will give you 12 possibilities, 12 alpha possibilities, different variations, right? And if you start with alpha, it will give you 6 different beta possibilities, right? So if you go from here to here, you end up getting 72 possibilities. Just a simple thermal cycling. Okay? A simple thermal cycling gives you 72 possibilities. And by the way, if you ask me why this should be followed, what is so special? Because this, if it is not followed, or rather if this is followed, the system energy is minimized. So those two phases, if I show you the entire crystallography of it, both experimental and schematic, you will find out that that is the one which is the most possible. Or if these two phases follow this relationship, then only the transformation will have minimum energy. Okay, so this is the problem. So these are all variants. These different colors are basically the alpha variants which are coming out of beta. Fine. Second thing you notice that they are not equal in number and not equal in size. Actually, that's what controls this entire texture business. Number and size. The number is controlled by a process, we call it variant selection. Certain variants out of this here, it's selected. They form easily, much easily over others. How and what, again, I am not going because that's complex. But believe me, some of them, not 12, all 12 of them forms with equal probability. It never happens. Only few of them always get a preference. That too, the ones which are forming, some of them enjoys a growth advantage and they grows larger and bigger and influence the texture finally. That's the connection. Okay? Now how it happens? That's a very complex process, how this one happens. If you look at a titanium lamellar microstructure, this is just a simple cast microstructure which undergoes a beta to alpha transformation. It gives you two types of alpha which are crystallographically the same, compositionally also the same, exactly same. The way they are different is the sequence with which they forms. So there is one which is called grain boundary alpha which forms the first. It's a grain boundary allotriomorph. If you want to know what is that, please refer to Potter and Esterling, phase transformation in materials. What is grain boundary allotriomorph? Basically this is an alpha phase and it forms at the grain boundary, beta grain boundary, first in the transformation, just because the grain boundaries are of higher energy and can take this transformation strain. They can accommodate the transformation strain much better compared to anywhere else. That's it. And then this intra-grainer, we call it intra-lamellar alpha. This one comes. That's what it shows here. Now point is, this is also alpha, this is also alpha. So this grain boundary alpha also undergoes same variant selection. Okay? And so as the lamellar alpha that forms. The problem is this entire process basically controls the variant selection, which variant will form. Just in simple thermal cycling. I am not even going to thermomechanical processing. Thermomechanical, when you apply some strain, then it becomes even more messier. Just a simple thermal process and you have such a complex process of microstructure development, rather microtexture development. Fine? Just one simple example. There are two possibilities with which this lamellar alpha can come out of the grain boundary alpha. One is called sympathetic nucleation, okay, where you have this grain boundary variants. By the way, as I said, grain boundary also have a variant, so you can see it in there. This grain boundary, this is one of the first work, very pioneering work from this Stanford and Bett in Actamat. They were the first people, I think in 2004, they published this work which first shed light about this grain boundary variants. So grain boundary variants are present, different size and number and all. The alpha phase is forming, but these two are not exactly related to each other in terms of orientation, and second thing, they will have some kind of a beta phase in between. Then there is another possibility, what we call interfacial instability. So this interfacial instability gives an alpha phase, lamellar alpha phase, which is exactly the same orientation at grain boundary alpha. Okay? And then there is an hierarchy between the two. This is a much easier process and need less energy, more preferred one. So if this one happens, this happens earlier than this. Fine? This happens earlier than this because this is slightly more energetically unfavorable. If this happens somehow, that somehow is again controlled by many different things. Why certain things will happen, why interfacial instability will happen, sympathetic nucleation, which are the cases, etc. But believe me, if this one happens, this enjoys a growth advantage because it forms first. And the materials world, phase transformation is extremely, extremely selfish. There is no socialism. If somebody generates first, grows bigger, they will just grow bigger. There will be nothing to stop them. Okay? So exactly that's what will happen. This guy will go and just completely consume the beta grains, most of them. The good news is this happens from many different, so one beta grain, if you see, it has many boundaries. So lots of colonies will anyway form from different sides and then they will impinge basically. Generally we tend to get within one beta in under normal conditions, variant selection, out of 12 possibilities 3, 4, 5 we get. If you get less number and more bigger size, you will get better influence from them on the texture, as simple as this. Okay, now the second thing, the grain boundary to lamella, first the grain boundary variant formation is not an easy process. That itself depends on many things. Just I will tell you why. This is simple. So when a grain boundary alpha forms, this guy when it forms, this guy, fine? This is formed between two beta grains. So it has to satisfy Burgess orientation relationship with both. Compared to this guy, which just has to do it only with one, its own parent beta. That's it. So this one, the situation is much more difficult. And that leads to many different situations, basically. How they will form and how many variants will form and so on. That's what it schematically shows, but that all those things are true. Proof is there that you can imagine different situations basically when the two beta grains, they are very close in orientation, etc. Then certain number and certain orientation of grain boundary alpha will form. Usually very less number of variants will form. When the two beta grains are quite different in orientation, then you have many more number of grain boundary alpha variants. And then when there is nothing, no similarity in their orientation beta, then you will definitely not get anything. And these three different situations of course will give you entirely different number of that lamellar alpha variants and their size. That's it. So just how the transformation is happening, how their orientation is getting detected, in which order it happens, will control finally the texture. So that's the connection between the microtexture and the final texture, or rather microstructure and final texture. And by the way this microtexture happens or microstructure forms will also control its properties. Not only the texture, fine? How many colonies are there and what is the orientation, what is their size, that also will control the properties. So it is controlling properties in one side, texture in other side and all. Complex business. And whatever the funny part is, whatever the mechanism that I told you till now is not always valid. There are other mechanisms as well. There are other conditions as well. Under those conditions, the beta orientation or misorientation will not be the deciding factor. So the deciding factor will be relative misorientation between beta grain boundary plane and habit plane. That also happens. Then the entire story that I told you proves wrong. Fine? It is so complex. But you understand that the message is clear here, that microtexture is extremely important. So it is basically the same thing. Now that is fine as long as you have a grain boundary alpha. Point is, sometimes you don't see or you don't get a grain boundary alpha. Like people who works with titanium alloys, they will understand this. So if you take a titanium alloy microstructure, you will possibly see 20 to 30% regions doesn't have grain boundary alpha. It just appears as if lamellar alpha is coming out on its own on the two different sides. Right? That's what we saw here, this kind of regions. It is coming out of its own without having any grain boundary alpha. The microstructure is so complex. For them, of course, there is some other kind of mechanisms that has to be there, that we follow. Then there is some other cases where the grain boundary alpha forms without following Burgess orientation relationship with any of the beta grain. That also is possible. So for them, again, there is a different altogether mechanism how the transformation will happen. And all these will finally tell you different type of structure. Then again, one more complexity. I'll just say, what if you have some foreign particles, foreign elements in the grain boundary? What if the grain boundary alpha doesn't form at all? You have something else. That also is a situation. And what happens when you have something else here is that it will change the complete transformation sequence through the change in chemistry, through the change in orientation relationship, all of this. It will change everything. And it will affect the final texture. So that's what I was actually having all this. We have a paper submitted in Jalcom. This is kind of summary from them that how this different factors that I was talking about, how exactly and they are influencing the bulk texture. So on and above the Burgess relationship and variant selection, how exactly this micro texture basically controls the texture, real bulk texture. That's the point, and this basically summarizes that entire thing. I am not going into that. Just one simple example of the complexity of the problem. Whatever I told you till now, okay, is only valid when there is a equilibrium or there is a very slow cooling. This is only valid for lamellar structure. You deviate from it a little bit, your story changes, entire thing changes. This is one work where we did nothing. We just compared a beta extruded with a beta forged. Just the deformation is different. The second difference is this one is slow cooled, this one is comparatively faster cooled. This is air cooled or not even direct air cooled, I would say somewhere in between furnace cooling and air cooling, die cooling you can say. This is a forced convection cooling, much faster. So this guy did not transform the usual way with grain boundary alpha and all those sequence and etc. It generates its own path, and as I initially said, basket web structure I don't want to take because it's a different story altogether. This is that story. That guy generates basket web structure, and if you see their texture, that's completely different, and that difference cannot be explained simply by extrusion versus forging, right? We all possibly have seen, okay, I think morning Satyam sir was talking about it, that different kind of processes will give its characteristic texture and so on. What he possibly didn't say that other things also can give it. Just you change this entire cooling rate conditions, everything will change. Okay, so that is one thing, and I think the second part I'll have time or should I wrap up? Okay. So second part is even more interesting, but I think Soumya and Arjun can discuss this even better. This part is basically telling you the texture evolution in alpha plus beta conditions. So what happens is this alpha plus beta conditions, if you roll something and you simply do a static annealing, you will see there is a completely different texture altogether in annealing. Just a simple thermal treatment changes the entire texture. So I am not going because this will take time. This is something called slip to morphology of this one, and then one new term that we call it orientation dependent spheroidization. So orientation dependent spheroidization basically controls here entirely this microstructure and texture evolution and all of this. So I am not going through this because these are all published and you can very well go through it. Just will tell you, maybe this one is important, another very good example of why you should consider microtexture, because the secondary processing and this orientation dependent spheroidization, that's process that I was just talking about, this has a real big impact in the aerospace industry. That's why we were once having this chance to work with GE Aerospace on one project with them. About MTRs is basically same a region of similar orientation, which is usually in the millimeter range, and that affects the fatigue properties. That usually is the center of crack nucleation, particularly in cold dwell fatigue, and that was so much difficult to avoid, and this was so impactful that GE engine fails and all of their aircrafts has to be grounded and so on. So they were desperately looking some solutions all over the world, and thankfully we were like knowing a little bit about that, why it was happening, and see things like that. But this is kind of an example how this MTR formation is kind of an, I would say, it gives a sense of feeling about that importance of microtexture formation and how it relates to bulk texture. Anyway, I am not going through these things. These are really difficult one to understand. Point is, just last messages that I wanted to give, that working in this field with the difficulties and challenges, I would say, on working with the field of titanium and working on the field of that microstructure. If you take any one of them, microstructure or texture, it is easier to do, honestly speaking. You have tools. You stick with microstructure, you have certain tools, go ahead. You stick with the texture, bulk texture, you have certain standardized tools, easier. And both the cases you go for a property measurement and you correlate them, easier. When you try to take your hands on both of these things, you need a fantastic characterizations to really do it, and this is just, this was not exactly meant for this was just a kind of summary of our present things that I was preparing for something else. But we are doing, in order to understand these various things about titanium alloys, we are doing high resolution TM at one side at here, IIT Kharagpur. I have a great colleague to do that. We are doing a lot of in situ testing. In situ testing is particularly important in this field, just because all of the mechanisms that I told you about transformation is happening at a temperature of 800 to 900, and all my characterizations are happening at room temperature. So it always, I have to extrapolate back. I have not many tools really to visualize what exactly is happening. That's the biggest challenge of working in the field of this kind of phase transformation. Everything is happening somewhere else and you are sort of looking at here. So things are happening in the sky and you are trying to see them while being in the ground. So that's the problem. So a lot of in situ efforts are happening. We are also having one such tool with us, in situ tool, in situ X-ray texture. So I think this kind of facility doesn't exist that often in most of the places, and we are lucky to have it, where we can actually have an alloy and just simply heat it up and measure it texture. So we have room temperature texture, we have high temperature texture, we can again cool it back, and so the cycle that I was telling you, so these two people, they have some nice results where you can see the complete pathway. Of course, I'm trying to do a lot of 3D characterization, because many of those this microtexture, again, the same problem is, whatever mechanisms, whatever conclusions you are trying to draw, statistics is a problem. And one of the reason for that low statistics is you are not able to see it. You are seeing the surface, you are not seeing what is happening in the bottom side. The other day I was reviewing a fantastic paper from Scriptamat, which unfortunately got rejected, but it was, they were doing some great characterizations with X-ray diffraction microscopy in the beamline, in a beamline, European beamline, and they were looking at this MTRs. They were able to see the shape and size of the MTRs in 3D, real 3D. So that kind of characterizations are very much needed. I'm trying that with Professor Tony Rollett, where I spend my sabbatical, but of course, X-ray microscopy, diffraction microscopy, etc. As I said, chemistry, in all of this story I didn't bring chemistry, but chemistry is also extremely important in that. Like for example, that why some grain boundary, some regions are not having grain boundary alpha and so on. These are basically chemical effects, what we think. So chemistry is very much important, and of course you have to talk to modeling people a lot, because without the modeling help, these days it's very difficult to really find out or kind of a validation of your mechanisms that you are proposing. So it is very difficult to do. We collaborate a lot with modeling guys, and this is the final message. I think most of the PhDs are here. So this is something I really like to show to PhDs. So this is the word from person who landed on moon. Small step by a man, a giant leap of mankind. And PhD Comics says, I don't know how many of you follow PhD Comics. He says, giant leap by one person, but a tiny insignificant leap by mankind. So the final message for us is basically the Sanskrit words that everybody knows, Charayavati, Charayavati. So get going and keep going and just try to understand about this titanium. That's what. Okay, so thank you. If you have questions. If you have questions, please go through those published papers. As I said, references are everywhere. And the second part, which I couldn't talk about, that for that students, please.
Thank you, Shivan. It was a very nice talk, very inspiring. We really got some ideas from it, and now we are going to take away some of your ideas. I would ask the students and the researcher, do you have any question? We have a very small time because Professor Samazdar is waiting. Okay, so we'll start his presentation at 4:30.
Sir, just one question. The variant you talked about, variant selection, you told that don't have not have equal probabilities.
Yes.
So is that the case of aluminum only, or other alloys? Titanium only, or other alloys which show this OS relationship between hexagonal and BCC?
Yeah, great question. Yes, this variant selection possibilities is there for everyone. Wherever you have this orientation relationship, phase transformation and all, the possibility of variant selection is there. Now if you, for example, as you said, aluminum. So aluminum, in case of aluminum, the theta prime, that also follows the orientation relationship with matrix. And they also forms in 3 different variants. Okay? But in those cases, the probability is almost equal. There is nothing basically that controls or that, if you are able to, if you add some microalloying, if you can do certain changes, you can change the nucleation. That happens. In some of the aluminum alloys, it does happen. So people just simply add some microalloying and then they change the nucleation probability. And then you change the variants also. Titanium, that's what I was trying to tell. So similarly, if you have a mechanism which has a preference for certain variants, yes, it will definitely happen.
Okay, so means if they have 12 variants, suppose in some other alloy, so there is possibility that one variant can overcome over another variant.
Very much so. Very much.
Okay, sir.
That's how, in fact, that's how slightly different context, but that's how abnormal grain growths happen. It's just a matter of chance that certain things grows big and big and big.
Thank you, sir.
So if something is getting a preference in a process, in a transformation process, if something is getting preference, and that preference is only cumulative, it will simply take it over. That's the thing.
Thank you, sir.
But if it is not favorable, that also, then it will simply diminish. That's the thing. Okay. Yeah.
Very nice presentation. And I will not allow further questions. I know that you might have a lot of questions in mind. So let us thank the speaker. And I would ask Professor Field to come and give this small piece of gift to Professor Shivendra.
Very nice presentation. I was stung a little bit at the beginning when you referred to me as the prior generation. So I don't forget that, but congratulations, very nice,
Okay.
very nice talk.
That's simply because, okay, I'll tell you why. It's not about age or anything. I'll tell you why I consider this, because I have seen papers from your generation. Because they are so obvious. You even give how many data points was indexed, what was the quality, and many other very, very small, tiny details. Because I believe that at your time, those were very, very important. We now even don't think, because it is just so understood. Still important. Yeah, but that's what, still important. That's the generation difference. Very nice. Thank you.
Thank you, Shivan. So, our next speaker is Professor Indradev Samazdar from IIT Bombay. Professor Samazdar may be online already. Yes. So, thank you, Professor Samazdar, for joining. I hope that you have a good, calm trip from Kharagpur to Bombay yesterday or today.
Yep. No, yesterday.
Yesterday. So, yes. So
see the
yes, yes.
following are the problems. Shongit asked me to present on a research topic which I have already presented. There was another topic which Shongit denied. So he told me something fundamentals. To me, the fundamentals are presented only in a teaching topic. So that's what I'm going to do. I use it. He asked me that why didn't you do extra diffraction, electron diffraction? Shongit, can you hear me?
Yeah, yes.
Okay. So why didn't you do extra diffraction as well as electron diffraction? Yeah, means one can present this thing also, an elephant. Elephants are good, but I prefer rhinoceros or hippopotamus. Now this is extra diffraction in a laboratory, a too shortened diffraction. So I'm going to talk about history and basics, instruments, minimum to know, this is bare minimum, standard X-ray intensity 2 theta, what to infer, texture and stress measurement, again minimum, and some kind of concluding remark. So number one, those who are with a physics background, if they did not look at a Crookes tube experiment, which was popular as an advanced scientific tool, 1869 to 1875, they should have a degree wapas, take back their degree, but that's okay. It is electric discharge tube with partial vacuum, 10⁻⁻⁴, 10⁻² torr. And electrons, the so-called cathode rays, they travel in straight line. One of the first things which you understand about X-ray is they travel in straight lines. This was in this time frame. Then comes this guy with unclean beard. His name, and he took a photograph which is called hand with rings. In German, hand mit Ringen. Of course, his wife was willing to do this, put the hand with the ring and take an X-ray. Those who are married, they should know this is an achievement, right? Shomjit, David, this is the Ronjan's first medical X-ray. 22nd December 1895, and this has happened. Now, what happened then? It became a roar. So people were getting their feet x-rayed, the nails on the boot. Society ladies in Trumpland, they were getting their hands x-rayed. There was a rage. Today it's possibly an equal rage. There are X-ray telescopes. There are, in the modern medicine, laboratory XRD, the tomography, or for that matter, this exotic subject of protein crystallography, all kinds of animal tomography, etc. So, X-rays became extremely popular. Almost all PhD students, experimentalists at least, will encounter X-ray some way or other. Now, where does the science start from? Science starts from this gentleman, von Laue. He told that each atom is going to scatter the electron, what was later called discovery of diffraction of X-rays by crystals. And when they're present as a plane, they will give spots. So a crystal structure based on, of course, transmission or reflection gives you a set of spots. Is it primitive? No. Trust me, because we use quite a bit of it, micro-Laue diffraction, to measure XRD stress of single crystals. And this is non-trivial. Then came this father and son. Their XRD machine is there, primitive in today's standard, but the philosophy is same. They told n lambda is 2d sine theta, path difference or whatever. Somebody I was collaborating in our physics department, Professor Shiva Prasad, told me once, and which I tend to agree. Laue is physics, condensed matter physics, whereas Bragg is material science. So Shivan, you're hearing this, you are in material science department. Now, what are the basic thing? They construct something called Ewald sphere. It's in reciprocal lattice space, where distance between each of these diffraction spots are actually atomic plane. Distance between the atomic planes gives you the d spacing. The Ewald sphere construction, which is S by lambda, it intercepts some of these reciprocal lattice thing and they meet the Bragg and diffract. So what we do is cheating. We make a very fine powder, run it through the X-ray. This is called powder diffraction. Remember, in this powder diffraction, only the single crystals which are meeting the Ewald sphere, the blue guys, they diffract. So this is, for me, is the history and basics, except for this slide. A typical XRD may look like this, but it's not too different from what the Bragg did. You put a sample at a particular height or Z. X-ray tube puts an X-ray at a theta, and this geometry is 2 theta, and you get it on the detector. So both tube and detector has the facility to measure, and this is the simple theta 2 theta measurement. You can make it more complicated. You can rotate the stage spin it, but your primary geometry is Bragg-Brentano, which is theta to theta. Of course, you have the ladle's geometry, which is the texture sensitive, and you have other geometries. We'll come to that. Now, we need to see the machine as it exists today. So I'm going to talk about, very briefly, about X-ray sources. I'm going to talk about the detector and the optics. So that's what the machine is. And of course, the goniometer. There are different X-ray sources. Cheapest, most popular is a sill tube. So you have a cathode, just a coil which is sending electrons to the anode, which is 4n or onward purity of any of these things. I personally run always with copper because I know the optics is all sensitive to copper. So this falls on the anode, generates X-rays of a particular wavelength. So what is this wavelength? Uncle Bragg, they told this wavelength is in lambda 2d sine theta. That means whether you are going to magnify or demagnify the difference between the d spacing. For example, copper is 1.4016 angstrom. Moly is 0.7106, if my memory corrects me. Oh yeah, numbers are here. So copper, whereas cobalt, oh, we have cobalt, is going to stretch the XRD peaks. Moly is going to squeeze it. Why people use different sources? One reason, ancient, is XRF. The another reason is depth of penetration also varies. Now, typically in a sill tube, you can rotate the tube, allow appropriate beryllium window to be functional, and get something called line focus and something called point focus. If somebody is doing regular powder diffraction, blind focus is your person. If somebody is doing texture stress, you have no option other than going to point focus. Reason I'll come later on the goniometer part. So you have different tube types, different focal length types, and so on. The second source is a rotating anode. This is medical X-ray primarily, but also laboratory X-ray. You have a cathode and anode, a combination, and this is going to rotate. If it doesn't rotate, heat buildup and damage is going to be tremendous. So to go to higher power, a sill tube, for example, a 3 kilowatt source, rotating anode can go to the tune of 300 kilowatt, some of the medical ones too. Another source is the metal jet or metal zoke. I was told by the folks who manufactured these that do not go for this. This is heavy duty. Good for tomography, not so much for diffraction. Last one is the micro source. This can be as low as 50 watt. We have a 50 watt source. Armed with multi-layer mirrors. So you end up putting at a very small spot lot of X-ray. Most important thing is the specific loading or beam loading. More than the kilowatt, focal spot is of course important, but this beam loading is important. Micro source gives you one of the highest beam loading, but only at a small point. That's all I wanted to talk about the sources. Next comes the goniometer. Crude drawing will be something like this. You have a movement on the tilt, psi angle. You have a rotation on the phi angle. You have X, Y, Z movement. 3 axis, 4 axis, 5 axis goniometer. Please be aware that there are all kinds of complication. I personally prefer using a goniometer with a source of laser, very small laser source, and a good quality camera mounted, so that I know where my X-ray is falling and I know how to get my diffraction done. So I can do a micro diffraction in this kind of setup. Of course, the goniometer has to be balanced very well by these screws. It also has a wonderful optical grating, which gives you a reproducibility. Ours is what? 0.0001 degree because of the optical grating. Now, next is optics. You have mechanical optics, less fashioned, but something like a knife edge can be wonderful. You have mechanical optics like a collimator. See, X-ray is not electromagnetic. So unfortunately, you can't focus. Focusing of the X-ray can be done by mechanical optics. What is the problem? Solar, the knife edge, or this guy, problem is it cuts. You lose too much of X-ray. Alternate choice is multi-layer mirror. Maybe a single layer, maybe the Montel, which I love, the wing mirrors. And if you are in a point focus, of course, the lenses, the polycapillaries and monocapillaries. Yeah, I wanted a 15 micron lens. They provided the one, but with a gap of millimeter. So this is not practical. So the mirrors and lenses, the optics, and finally the detector. There are three philosophies of the detector. Whether it's a microlave, single crystals, or it's a polycrystal, you can do a 0D detector, any one of these points. Problem? You miss out most of the points. 1D detector, come on, which is a line. You see the entire thing. Or a 2D detector, where you will be seeing the entire area. So the multi-scale, multi-channel, solid-state 2D detector can be a wonderful tool. It almost reproduces your Debaucheer cameras of ancient time, but you can do it. Remember, you have the gas proportional counter. You have the scintillators. Scintillator has better energy resolution. You have something like a micro gap technology, which is obsolete today. We use it, Ventec. Or you have a choice of a fiber optic based, very nice solid state detector. Maybe your Galipix, maybe your Eiger, if you have a lot of money. All these can be done. Ultimately, what you are getting is an XRD pattern. In a powder sample, not you. In a powder sample, each of these things which are satisfying, meeting the brag, they give you a peak. So what's important in the peak? Peak to background. So a lot of people change targets. I know folks who does that on a routine basis. I'm talking about so-called big multinational companies. Foolish. Because when you change the target, your optics, which is all important, is geared up for one target. It doesn't change. The coatings on your mirrors and lenses do not change. What else? You can do what I love doing is PHP cutoff. We were doing monochromator till few years before, but we are now more comfortable with the pH cutoff. If you know the X-ray thing, you can do, come on, you can do this PHP cutoff, take out the XRF, even take out overshooting things. Now, if you can do your optics Source is fine. What is the other issue? Energy resolution. What else? Peak to background, energy resolution, and error, which I will call as delta theta. So each of these peaks can have a fudge factor. One of them comes from source. Of course, delta theta 1, of course, you can reduce it by putting maybe a double bounce monochromator, but your intensity will go to the toss. Your Gunn emitter, to reach this, you should have the height calibration. Or if it is a single crystal, you should go to appropriate tilt and rotation. That's what we do with the microlave. Other thing which you need to look at is what your material is. Crystalline structure, you get clean, nice X-ray. Liquid or amorphous solid, bit broader. Even monoatomic gases, at least Raman Research Institute, they do this. Or amorphous solid with crystallinity. And there is air scattering, so but it's oversold. This is what you get in a intensity 2 theta measurements. Now you have a nice XRD peak. What are you going to do? Remember, in practical material, your XRD peaks are not always nice. This is Ashish's paper, 2022 vintage. This is niobium. On top of that, you have 2 niobium oxide, monoclinic and triclinic. So you go with your microfocus, area detector, measure the XRD, not you. Measure the XRD peaks. Trust me, this took us hell to get them identified. What we do is called a Rietveld. It's actually, you get this lines, intensity profile lines. They are called Rietveld, most of a fast Fourier transformation. You identify the peaks. Of course, I would do a better job manually, but whatever, you do the Rietveld. Now you want to do a quantification. So you put a complex polynomial like this, what is called RWEP, and you fit a different RWEP between experimental and your predicted profiles. You can fit them and go to a reasonably lower thing. Why do you go through all these problems? This is your EBST. This is iron and oxide. This is your iron map. This is your oxide map. You will be noticing that everything is identified as iron, but some of them, even with whatever indexing you do, this distinction needs to come with composition. Now, Rietveld is extremely effective, but it can give you complete nonsense like any other technique. For example, this is the land of the king and queen, British penny. They're cheating. They're giving you a penny which looks like copper, but it's actually electroplated copper on a piece of iron. You put the XRD, laboratory XRD, and you get copper peaks. Nice copper peak with copper target. Do a bit of polishing, get the copper out, most of it. You now see copper peaks and a very strong background. This is your fluorescence, and it's real. As I told you, initially, at initial days, we were running with a different target. Then we gave up. We started using a calf crystal monochromator. Very good, but intensity drops. Finally, we went to the PHP. And I would live with the PHP if I'm using a solid state detector. So what does the intensity come from? These factors. Structure factor, the Lorentz factor, polarization, absorption, and thermal factor. Combine everything, it looks like an equation of this kind. This is only the structure factor. The other factors are real. So you want to measure what? Retained austenite in iron? Very common thing which comes. They will tell, oh, we have a Rietveld, and it will do that. In fact, most of my students are lazy to use a Rietveld. But if I were you, I would be fitting the individual factors. They are fairly standardized, and use that. So there are existing practices, many of them, they use different targets. I strongly think, and we have tried that. Steel sample with a copper target, but a monochromator. On the ODF space, you gain about 20%. Steel sample with a copper target with pH cutoff and proper solid state detector, you get 40% gain. So between monochromator and filter, I would prefer filter, but PHP is now what will be my choice. The detector setting and type completely depends on your application. Completely depends on your actual, because if I'm running the GI, I won't use the wanted area detectors. They will be nonsense. Optics, again, depends on your application. Microfocus, we have no choice other than using the Montel. On any other application, on the other machine, cell tube machine, we use lens, monocap, and polycap. The most important thing is data quality and data integrity. Remember, you have a thin film as deposited. X-ray will show it as amorphous. Electron microscopy will show it as crystalline, because X-ray peak broadening, etc., depends on the dislocation density. Of course, peak can shift, but the entire peak thing depends on this kind of Unger type of equation. It has a component of size, but that fortunately goes to nanocrystalline range and the defects. You can look at C by A ratio, fairly routine. You can measure very accurately the stress-free lattice parameter, something I would like to use it in conjunction with the EBST in coming days. You can look at elastic plastic strain energy. How much is the energy associated with the dislocations present? I call it as X-ray resolution function. Looks simple but non-trivial. You have to take out the safety. And you can separate the K alpha 1, K alpha 2. When the elastic plastic strain energy doesn't mean only dislocation density. It means energy associated with the dislocations. And this separated. You can get your XRF done, and it's extremely good reference for recovery. So more than traditional phase idea and quantification, all these applications are there even for theta to theta XRD. And you have a whole world of texture and stress. If you have these lines, for example, we can look at this and tell these are big spots, so big single crystals. Please oscillate the stage more. You can get this funny kind of XRD. If you leave it to your commercial software, they will kill this background and you'll be missing many things. You can look at preferred orientation, even stresses. We do quite a bit of things on the stresses, so I'm keeping on talking about this. So an X-ray, where you can do all these jigs. You have a detector, you have all kinds of anti-scattering slates, you have the receiving slates, horizontal slate, vertical slate, and X-ray source. And you run and tilt your measurement. You can get the so-called stereographic projection or equal area. Everybody talks about equal area, but I don't think anybody does that. So this is cheating. And you can do all this rotation and you can get an XRD. In the XRD, of course, you can measure any of those paraphanias of so-called crystallographic texture. In today's graphics, you can plot the ODF in 3 dimensions. This is all doable. You can look at a microstructure. Depending on the grain size, and I think this is Hitesh's IF, this is big grain size, you can go and do a lot of stuff. Look at the stresses, look at which we do as the magnetic properties. Look at the R values. Look at the texture, how it is varying. Or look at the stresses. So we use 2 systems. One is a standard Empyrean, but this is with a already in cradle. And we use our Bruker's T8, which comes with a micro source. 50 nanometer is a minimum we can go, and of course, an area detector. This has multiple detectors. In this configuration, I think it can picks. So we can measure it. There are 2 ways of measuring stress. Not 2 ways, more. I'm coming to that. One is standard d sine squared psi. Why do you use that? This is cheating. There happens to be, you don't know d0, so you are measuring from the slope of d versus sine squared psi, the stress, tensile and compressive stress. You look at this separation, which is called phi splitting, and you measure the shear stress. This is in plane normal stress, out of plane shear stress, epsilon 1122 or epsilon 13. This is only for one pole. If you want to make it depth sensing like a sensor, you want to go lower and want to see how much is the distance from the top of the sample, top coat, bond coat substrate, which you have been doing. You can do this, and you can do it in what we call as multiple HKL GIXRD, grazing incident X-ray diffraction. And you can measure for all peaks these things. A word of caution. There are algorithms for identifying automatically XRD peaks. If you are using a commercial algorithm, best is to use the Bruker's one. But none of these algorithms work very well. So peak shift identification needs manual intervention. So I normally get the stress done with one swoop. Otherwise, you are heading for a problem. Of course, there are much more. You can do the stress by micro-Laue diffraction, which I told you. You can do it for the entire space. You can map something for stress, like this part of the weldment. You can plot the dislocation density and stress in the Euler space. So you just follow the ODF pole figures. So all these can be done. You can measure, and this is non-trivial, track shear residual stress. More importantly, the hydrostatic stress by XRD. Non-trivial, but absolutely beautiful. You can do a tensile deformation and track the development of residual strain. Remember, by these diffraction-based techniques or any technique, you only measure strain. There is no stress meter. You can do all this. So this is something which we do with the micro-Laue, and I believe we can do it with the ambiguity of the HRD BSD stresses, because we can piggyback. We'll see that. So all I presented to you, and I know you have a validatory program. Shongit owes me some party sometime else. A bit of history and basics I have given. I gave you some details about the instrument. Why? Because unless you know the instrument, your X-ray has no meaning. I gave you something on intensity and on the peak profile. No, bit on texture and stress. This is definitely cramped for an introductory lecture. But my apologies. Sometimes you need to do a cramping, and I think I'm done. So, you have any questions, I'll be more than happy to answer. Yes, sir.
Thank you, Professor Samazdar. If you have any question, please.
Shomjit, otherwise, if the students do not have questions, tell them I have prepared a detailed tutorial question, a quiz. Right? I told you. You will be handing over the quiz. Right? Nobody raises a hand. Shomjit, your problem. If nobody raises a hand,
No, there is
then
one
I'm
question, but yeah, mic is working.
Good evening, sir.
Yeah, please.
Sir, I have a question. Like you talked about factors affecting this diffraction intensity. So how they are related in case of X-ray diffraction and electron diffraction?
Hello.
That's my first question.
So, number one, the factors for electron diffraction are completely different. Let me be more specific. There is a structure factor and scattering factor for electron diffraction. It's different from X-ray diffraction. Electron diffraction is more the diffraction contrast, diffraction pattern comes either from kinematical contrast, which means no interaction between the beam, or dynamical contrast, where it means there is a difference between the beam. Your question, more valid question, would have been, we have X-ray diffraction. And remember, solving an unknown crystal structure, there are tools in the electron diffraction. For example, the tomography in this thing, 4D10, they can do unknown crystal structure. But if you have seen the expertise needed for knowing an unknown crystal structure from electron diffraction, it is really bad. X-ray diffraction, of course, the only way to do is the so-called single crystal X-ray diffraction. More of a microlave in multiple planes. It's easier. Number two, the primary difference is X-ray diffraction for texture, stress, orientation, blah, blah. Best which you can do, what I know of is the Rizzo guys were doing at 5 micron resolution, spatial resolution. Tomography, you can go to nanometers, but not these measurements. Electron diffraction, on the other hand, you can do HREBSD about 20 nanometer. TEM can be 1 nanometer or lower. So X-ray diffraction and electron diffraction. X-ray diffraction also has slightly questionable measurement uncertainty, reproducibility, angular resolution. So if you are asking me, this is bigger scale, more well-defined than this. Why? This guy is showing me angular resolution. Okay. This foolish watch. So this is the difference. Did I answer your question?
Yes, sir. Sir, I have 2 more questions if you would like to take.
Please do.
Yeah. Sir, you talked about the micro diffraction. Sir, what is the typical beam diameter in that micro diffraction?
What we can achieve in our system is 50 nanometers. 50 micron, I'm sorry. 50 micron, that is what we can achieve.
Yes, sir.
I don't think anything lower than that is doable, except with a synchrotron intensity. And there you can go to 5 micron. Remember, however, by this 50 micron kind of intensity, and we discussed it many times. Microlave, we are the only guys, which I was telling to David earlier, in the world who does it on a laboratory XRD. There are one group in Kobe, one in Grenoble, who were doing it on and off with a synchrotron. And it's extremely manpower and expertise driven. So we never do provide this service to anybody. It is 50 micron, takes ages because you need to do a calibration between EBSD orientation and the goniometer orientation. Of course, tracking, etc. is there. And to solve the orientation or the stress tensor, you need 6 diffraction spots. Okay?
Yes, sir.
50 micron.
Sir,
Next question.
another question is like, related this intensity only, you talked about 4 delta thetas.
This is the error.
Yeah, means
So what
one,
you are measuring is the position of an X-ray peak. Your D-spacing measurement or anything is position of an XRD peak. They normally tell you this position depends on peak broadening. Of course it does. But in addition to that, there can be errors in the measurement. For example, if your lambda is not very fixed, you are going to have plus minus delta lambda. That's a disaster. That is the reason first of all, people like synchrotron other than the beam intensity. These are intrinsically lower delta lambda. So a laboratory guy, means those high-res guys, the physics guys, they would prefer using a double bounce monochromator. Our physics is buying a new machine. I was there involved. So this is the right thing to do. But your intensity will go for a toss. So this is on the incident side. I prefer using lens because most of our work is point focus. Next comes the goniometer. If you are not, see, Bragg only talk about D-spacing, but this is in 3 dimension. So if you are not in exact Bragg in 3D, because it's not Ewald circle, it's Ewald sphere, you are going to be off. Third is on the detector side, the receiving optics. My personal preference is anti-scattered slit, programmable, so which is very reproducible. A Solarts 04 or 02, based on what we are going to do. Then comes the detector. There are different choice of detector. Each one of them has their energy resolution and other things. If I'm using an area detector, my issue is angular resolution as well as a Bragg angle, which I'm going to cover. All these components have a built-in error. How much tolerance on the theta measurement they can do. These are the 4 thetas. For example, you are measuring a peak at 22.1 degree. Your 4 thetas gives you 22.101. You may tell that small thing has no meaning to me. 0.001. For many applications, you may need 0.0001, 0.401 kind of thing. This is the absolute error on the X-ray diffraction. Am I clear?
yes, sir. Thank you, sir. Thanks.
Does it answer all your questions?
Yes, sir.
Somjit, no more
Thank you, sir.
questions.
Is there
I'm
any
going to
more?
ask you questions.
Is there
I'm
any
going to
more
ask you
question?
questions.
Yeah. Who? Anybody? No more questions?
Martin side would have been a huge kill.
Okay, Indra, I
Never
have
came.
to ask a question because you gave me a hard time
Sure,
when I
sir.
didn't ask you a question the other day.
Sure. See,
So-
David, I was getting extremely
So,
disappointed, thinking that
good.
the famous Professor David Phil
Good.
does not ask questions.
Thank you. So,
Please tell me.
first, I should point out that you are from the prior generation. I just point that out because you and me are from the same generation.
I started with my hand metering.
Anyway, so I was speaking
I'm
with
ancient.
I was speaking with Dorta just before Christmas, and she said that she has just put in a patent application for 1 micron resolution on synchrotron. So she says she has it improved by a factor of 5. So she wouldn't tell me how that's done. So if you have any thoughts of how that might be done, I'd be interested in that. But
See,
But
there are
wait, let me
only
just say one more thing first. But
Sure.
residual stress measurements, generally, as you were talking about, always require this kind of reference, unstrained reference in
Yeah.
pretty much all the techniques we use. And you and
Yeah.
I talked a little bit about simulated reference versus trying to measure a reference. And just any thoughts about the very best way to get that unstrained reference in any technique is, I think, a huge challenge for us, and would really, if we could do it right, would really give us a leg up or a good advance in residual stress measurements that we could actually believe. So, comments on that?
Okay. So I'm taking the questions, David, in the reverse order. Your first question is D0. See, number one, in a D sine squared psi measurement, which was originally being called as 2 exposure measurements. Even now, those idiotic portable machines, that's what they do. They have 2 PhDs in 2 locations, and they draw a straight line out of 2 measurement points. I had a question, never got answered, that if you are really imaginative, you can draw a straight line with 1 point. But this does not need a D0. Why it doesn't need D0? It basically extrapolates the D sine squared psi measurement. What you are seeing here is an extrapolation. Then it uses this extrapolation and a continuum elasticity equation. You can look at, possibly the best reference is Paul Vanotta had an overview on stress measurements. Multiple HKL GIXRD, we piggyback on the same concept. However, if you want to do a triaxial stress measurements, see, these are all biaxial. But real fun is with the triaxial stress measurements. Your failure is decided by that. If you want to do this hydrostatic stress measurement, but XRD, then you need to have D0. If you want to do micro lave, you need to do D0. So what we do is the D0 is the following. We get the finest powder of the same material on which we are doing the measurement. We vacuum seal it completely, high vacuum, even with the parting of argon, put it in a furnace for eternity, make sure it's fully annealed, recrystallized. Even that is not a guarantee it will be stress-free, but your trick is to have the finest powder. Then you do an XRD on this fine powder. Based on the crystal structure, you still need to take out the contribution from different types of stacking faults, etc. Recipes differ between FCC, BCC, HCP. Lower than that, I have no clue. Where do you get the recipe? See, Maurice Cohen had a student called Nguyen. People all talk about Kaliki for XRD book. My colleague, right now I'm teaching a course on electron microscopy, electron diffraction. This colleague teaches on X-ray diffraction. He will go with Kaliki. In my opinion, if you want to do this complicated thing, please look at the Noen's book. Most of the thing is explained and explained well. Similarly, if you want anything on the instrument, look at Bovey's book. So, summary. D0 can be measured experimentally. It is extremely painful. So you do the D0 measurement only when we need to do that. So one of my ambition, David, is to get the D0 done. From the D0, you can get the ABC, alpha, beta, gamma, input it to simulate the HREDs and use that as reference. Now, coming to the second point, that how Dotte is claiming that she will be able to go to 1 micron. Dotte has claimed that crystallized grains are coming from wherever, which is not possible. Energy does not allow that. But it is possible only with breakthroughs in X-ray optics. Synchrotron on the Grenoble, they already have a huge source or detector. I know for sure that Grenoble does lot of innovations on X-ray optics. Single layer mirror, because this unit, Sanox, it's a lovely unit for SATs. But I don't think there has been any recent development. Because remember, they are doing this 5 micron or 1 micron on the 3D. Attenuation is tremendous. I don't think at this moment technology exists for doing that. Claim? Oh, one can claim anything. I'm sounding a bit harsh, but I'm telling you the facts. These are my subject is X-ray and electron diffraction. I understand it well. Right, David?
Absolutely.
Hey, you need to come to Bombay.
And she and she wouldn't tell me exactly what was going on, but it has to be in the optics. I think so too. I don't think it's just an algorithm.
See, the detector resolution, detector has certain problems, very fundamental problems. Detector's fundamental problem is the guys who are making these detectors are different from the users. So the primary problem is addressing the pixel points. So you, in the best detector which money can buy is Eiger. Eiger, you actually take a photograph of the detector thing and they deconvolute it. Gallipix that way is better. The paralegals are even. Now detector, I don't think there is a breakthrough. You just can't handle those many data points. Energy resolution has gone for a toss. The only possibility is optics. And if there is a new optics from Grenoble, they have beautiful optics, and I know some of that. You will hear about it.
Okay, so I'm going to yield, and if there's anybody has final questions, I'll let them ask.
Nobody is asking me questions.
Yes, they are afraid of you.
Hey, you didn't show me my biopic. Did you show my biopic?
I don't have it now.
Okay, this is an excuse.
Yeah, it was beautiful.
Okay, all right.
So there is no question further, right? Is there any questions? So
I'm disappointed. But you,
yeah, there is.
There is. You got, huh?
There is.
Okay. Otherwise, I'm going to shoot the tutorial question.
That would be great too.
I want to ask that I have. Oh, sorry. I want. Hi, sir. My name is Auditro and he's Rajdeep. I want to ask that X-ray, how we can measure the stacking fault. I have not done X-ray course, but I want to know how X-ray can measure stacking fault and 2D defects in the laboratory scale. Can you please elaborate on
See,
that?
the stacking fault measurement, again, I would refer you to not Kaliti but to Noyen's book. It's curve fitting. So what you assume is certain type of intrinsic stacking fault. It can't do extrinsic stacking fault.
Okay.
And from the profile of the peaks plus tractionality, see, you can estimate the stacking fault energy. Is it accurate? The only thing I think measures stacking fault energy accurately is composition-based empirical rules. In the modeling, DFT versus MD, there are a lot of issues on stacking fault energy. So can X-ray measure stacking fault energy? A lot of people claim yes. I'm not too sanguine if it does. I won't do it. Dislocation density, yes. Separation between individual peaks in the orientation space, yes. Stacking fault energy, I have been following. There was a time when I was breaking my head. No, I'm not convinced.
Okay, sir.
Does that answer your question?
Yes.
Any
So
more questions?
unfortunately, no. Yeah.
Yes. No questions? Yeah.
Hello, sir. My name is Sampreet. Sir, you told measurement of dislocation density we can measure from XRD. It is highly reliable, but there are so many things can.
I never told highly reliable.
Okay.
I never told.
Oh, sorry, sir. Sir,
So
how?
what I told,
So that
very first thing on the XRD, which you will find in Kaleti's book, is they were measuring from FWHM. They were telling this is probably scales with dislocation density. Beyond Kaliti's this claim, FWHM scales with hardness. That's a word which was used in Kaliti's original book. Beyond that comes the Stibitz. So Stibitz fits it with an empirical formula in which he tells this will be the stored energy. People have used it. Next comes what you can call as Williamson-Hull, very popularly used BR cos theta equal to sin theta. Intercept that scales with the grain size, slope scales with this. All these has a problem. It is extremely subjective to the anisotropy. So dislocation density, there are two ways to measure it. Let me go to the slide. So we have been using at one time Vijay's papers and others, Williamson-Hull, not too happy. We have been measuring dislocation density in two ways. Variance, where you take all the peaks, do a scaling, or individual peaks. Look at the profile of the peak.
Sir, we could not see the slides. Just a second.
You are not seeing the slides?
No, sir.
Cheating. Now you are able to see the slide? You can see the slide?
Yes, he wants to see the slides.
So this is the equation. So in Ungar's book, or for that matter, my book, but Julian wrote this section, you can see this. This is second order moment. It scales with Q and dislocation density and grain size. But if it is beyond nanometer, you can measure dislocation density. Ungar proposed asymmetry of the peak will give you different nature of dislocation that I would question. But this has been verified. Remember one thing, GNDs are doable. They will tell you how. SSD is only ECCI and that can be a real pain. Questionable. So if anybody tells you we measure dislocation density by TEM, you tell him he is hallucinating. We do that at times, but he is hallucinating. This is the only quantifiable way. Fit a second order moment Fourier series from the slope normalized. And very often we use rho normalized. We don't use the absolute value of rho. Why? Because absolute value has no meaning. So trend in dislocation density can be resolved, not exact quantity. If I told you exact quantity, I think I was dreaming, daydreaming. Strange. You can daydream without. Okay? Does that answer your question?
Yes, sir. I have one more follow-up question, if I can.
Sure, please do.
Sir, like if I wanted to calculate the dislocation density, how much should be my peak intensity to get the?
See, Unger talks about an abnormal number. I would go with lower number. Remember, peak to background is 2 square root bt. This is the background, T is the time. Okay. But you can go, these XRDs, let me see the data, you can go very high in peak to background. We normally operate in 10,000:1 scale.
Okay, sir.
So this is the reason you need the optics and the detector.
Okay.
Because to get the best possible peak to background. Am I clear?
Yes, sir. Thank you, sir.
Okay. Any more questions?
Any more questions?
David had one more question. He told me he will ask.
Do you?
I think it's your bedtime, I believe. So I don't have any more questions, Andrew.
Yeah, not bedtime. We invited somebody who will have dinner. But
you've been traveling. You're tired.
See, it was very painful yesterday. Not that car. But I think I'm getting claustrophobic in the aircraft. So we should bring back hot air balloons.
Some are trying to do that.
It's a good idea. Do you know there was a bus trip from London to Calcutta?
Yes, yes.
It was a beautiful bus trip. They stopped in 1976 because of unrest in Middle East, Iran primarily. Mm-hmm. So you can take the bus from London and you can drive, I think, 49 days. It should be good to do that. Sangeet, you want to be party to that bus trip?
Yeah, maybe, yes. Maybe yes, right. Once.
David, you are a willing soul?
Always willing for an adventure.
Yes.
Willing for an adventure, I'm right again.
Yes.
If he comes, okay.
All right. Sangeet, later let me know how much of it did sink in.
Yes.
I told you Martin site would have been an overkill.
Yeah. Oh, yeah. No. This presentation was very good, and this is, I think, it was fundamental, though it was hard for the students. I understand that. So I just
extra distraction. Why should it be hard?
I just would like to say my students that see how I make things easier for you. It's not that easy what you think. It's really complicated.
Okay.
Yes.
Okay. All right. Okay.
So thank you.
See you guys.
Thank you, Professor, Bye. For giving this wonderful lecture. We are really glad that you considered our invitation with your such an hectic schedule.
You told me at the last moment. I didn't forgive you for that.
Yes, I owe you. I owe you a good, we'll what you called a grand dinner or something like that. I owe you.
Nah. Dinner is passing. Okay.
Okay.
All right.
Thank you, Professor. Thank you so much. Thank you. So it was a long evening, and Professor Samazdar, as you know, that he is one of the very, very renowned and senior researcher in this area. So his talk is really to something that we should now go back and read our books, okay? So, so I hope that you will join tomorrow at 9 a.m. Professor Field is going to give another talk, and this talk would be something a little different because it will be on triple junctions, right? Boundaries and triple junctions, which we really need to know and we don't consider till date in metallurgy most of the time. But since soon things will be most of them nanomaterials, and so there would be lots of triple junctions. And then we will not be able to avoid the properties that are going to affect due to multiple increase in the triple junctions, right? So please don't avoid that lecture. There is coffee outside and there are, I think, lays. So that's it. There are dinner coupons with Shomadip. Please take them. We will have dinner from 7:30 in the TJH guest house, right? Disperse.